Hello and welcome back to the course on deep learning. Today we're talking about the neuron, which is the basic building block of artificial neural networks. So let's get started. Previously we saw an image which looked like this, and these are actual real-life neurons which have been smeared onto a glass and colored a little bit, and they are observed through a microscope. So this is what they look like. As you can see, quite an interesting structure, a body, and then lots of different tails, kind of branches coming out of them. And this is very interesting, but the question is, how can we recreate that in a machine? Because we really need to recreate it in a machine, since the whole purpose of deep learning is to mimic how the human brain works, in the hope that by doing so, we're going to create something amazing. We're going to create an amazing infrastructure for machines to be able to learn. And why do we hope for that? Well, because the human brain is just happens to be one of the most powerful learning tools on the planet, or like learning mechanisms on the planet. And we just hope that if we recreate that, we'll have something as awesome as that. So our challenge right now, our very first step to creating artificial neural networks, is to recreate a neuron. So how do we do that? Well, first of all, let's have a closer look at what it actually is. This image was first created by a Spanish neuroscientist, Santiago Ramón y Cajal, in 1899. And what he did was he dyed neurons in actual brain tissue and looked at them under a microscope. And while he was looking at them, he actually drew what he saw. And this is what he saw. He saw two neurons, or two large neurons over there at the top, which had all of these branches coming out of them towards their top parts, and then each one of them had this rod or like thread coming out towards the bottom, very long one. And so that's what he saw. And now, technology has advanced quite a lot, and we have seen neurons much closer in more detail, and now we can actually draw what it looks like diagrammatically. So let's have a look at that. Here's a neuron. This is what it looks like. Very similar to what Santiago Ramon drew over here. And here in this neuron, what we can see is that it's got a body. Well, that's the main part of the neuron. And then it's got some branches at the top, which are called dendrites. And it's also got an axon, which is that long tail of the neuron. And so what are these dendrites for, and what's the axon for? Well, the key point to understand here is that neurons by themselves are pretty much useless. It's like an ant, right? An ant on its own can't do much. Like 5 ants together, maybe they can pick something up, but again, they can't build an anthill. They can't establish a colony. They can't work together as a huge organism. But at the same time, when you have lots and lots of ants, like you have a million ants, they can build a whole colony. They can build an anthill. Same thing with neurons. By itself, it's not that strong, but when you have lots of neurons together, they work together to do magic. And how do they work together? That's the question. Well, that's what the dendrites and the axon are for. So the dendrites are kind of like the receivers of the signal for the neuron, and the axon is the transmitter of the signal for the neuron. And here's an image of how it all works conceptually. So at the top, you've got a neuron, and you can see that its dendrites are connected to axons of other neurons that are like even further away above it. And then the signal from this neuron travels down its axon and connects or passes on to the dendrites of the next neuron. And that's how they're connected. And in that small image over there, you can see that the axon doesn't actually touch the dendrite. A lot of machine learning, or like a few machine learning scientists are very adamant about the fact that it doesn't touch. It doesn't touch. It has been proven that there is no physical connection there. But the point that we're interested in is that connection between them, that the whole concept of the signal being passed, that's called a synapse. You can see over there in that little image, that's figure bracket is a synapse, and that's the term we're going to be using. So instead of calling our artificial neurons, the lines that we're going to have, or the connectors for artificial neurons, we're not going to be calling them axons or dendrites, because then the question is, whose connection is this? Is it that neurons, or is it this neurons? We're just going to call them synapses. And that's kind of just answers all questions right away. That's just basically where the signal is passed. Doesn't matter who that element belongs to. That's just a representation of the signal being passed, and we'll see that just now. So basically, that's how a neuron works. And so let's move on to how we're going to represent neurons, or how we're going to create neurons in machines. So we're moving away, now we're moving away from neuroscience and moving into technology. And here we go. So here's our neuron, also sometimes called the node. The neuron gets some input signals and it has an output signal. So dendrites and axons, remember, but again, we're going to call all these synapses. Then these input signals, we're going to represent them with other neurons as well. So in this specific case, you can see that this neuron, this green neuron, is getting signals from yellow neurons. And in this course, we're going to try and stick to a certain color coding regime where yellow means an input layer. So basically, all of the neurons that are on the outer layer or in the first front of where the signal is coming in. And by signal, it might be like a bit of an overkill to call this a signal. It's just basically input values. So you know how even like in a simple linear regression, you have input values and then you have a predicted value. Same thing here. So you have input values, and there they are, the yellow ones. And then on the right, you'll see just now, it'll be red. It'll be the output value. The thing that I wanted to point out here is that in this specific example, we're looking at a neuron which is getting its signals from the input layer neurons. So they're also neurons, but they're input layer neurons. Sometimes you'll have neurons which get their signal from other hidden layer neurons, so from other green neurons, and the concept is going to be exactly the same. And just in this case, we, for simplicity's sake, we're portraying this example. And in terms of the input layer, the way to think about it is, in the analogy of the human brain, the input layer is your senses, right? So whatever you can see, hear, feel, touch, or smell. And of course, it's like there's a lot of things you can see. There's a lot of information coming in, but that's what your brain is limited to. It's pretty much it's pretty much lives in a box made out of bones, and it's a mind-blowing concept to think about, that your brain is just locked in a black box, and the only thing, like, it can't see, it can't hear. The only thing it's getting is electrical impulses coming from these organs that you have, which are called your ears, nose, eyes, your sense of touch, and whatever, and your taste, right? So it's just getting signals, but it basically lives in this dark black box, and it's making sense of the world through your senses. It's phenomenal. And so you have these inputs that are coming in. In terms of human brain, those are your 5 senses, and in terms of machine learning or deep learning, that is basically your input values, so your independent variables, and we'll get that to in a second. So your input values, the signal is passed through synapses to your neuron, and then your neuron has an output value that it passes further on down the chain. In this specific case, in terms of color coding, again, yellow means input layer. So we're kind of simplifying everything here. We're saying we're only going to have like the input layer, then we're going to have one hidden layer with the green, which is the hidden layer, and then we're going to have the output layer right away. So just so that we can get used to these colors for now. So there we go. That's the basic structure. So now let's look in a bit more detail at these different elements that we have. So we've got the input layer. And what do we have here? Well, we have these inputs, which are in fact independent variables. So independent variable 1, independent variable 2, independent variable m. The important thing to remember here is that these independent variables are all for one single observation. So think of it as just one row in your database, one observation. You just take all of the independent variables, maybe it's the age of the person, the amount of money in the bank account, and then how do they drive or walk to work? What method of transportation do they use? So, but that's all descriptors of one specific person that you are either you're training your model on or you're performing some prediction on. The other thing you need to know about these variables is that you need to standardize them. So you need to either standardize them, which means make sure that they have a mean of 0 and a variance of 1, or you can also sometimes, and Hadlan will point out these situations in a bit more detail, perhaps in the practical tutorials you might come across these. Sometimes you might want to not standardize, you might want to normalize them, meaning that instead of making sure the mean is 0 and variance is 1, you just take you subtract the minimum value and then you divide by the maximum minus the minimum, so by the range of your values, and therefore you get values between 0 and 1. And it depends on the scenario. You might want to do one or the other, but basically you want all of these variables to be quite similar in about the same range of values. And why is that? Well, all of these values are going to go into a neural network where, as we'll see just now, they'll be added up and multiplied by weights, added up, and so on. And just going to be easier for the neural network to process them if they're all about the same. And in fact, that's just how it is going to be able to work properly. And if you want to read more about standardization, normalization, and other things that you can do with your input variables, a good additional reading paper is called Efficient Backprop by Jan LeCun, 1998. The link's over there. So Jan LeCun, we're actually going to talk more about this phenomenal person in the space of deep learning in the part of the course where we're talking about convolutional neural networks, and you'll see that this is definitely a person who knows what he's talking about. He's a close friend of Geoffrey Hinton, who we've already seen, who we've already mentioned. So in this paper, you'll learn more about standardization and normalization, but also you can pick up lots of other different tips and tricks, and it'll be a good source for additional reading as you go through this course. So yeah, check it out if you're interested in some additional reading. There we go. So that's what we need to do with the variables. And here we've got the output value. So what can our output value be? Well, we've got a couple of options. Output value can be continuous, like for instance, price. It can be binary, for instance, a person will exit or will stay, or it can be a categorical variable. And if it's a categorical variable, the important thing to remember here is that in that case, your output value won't be just one, it'll be several output values, because these will be your dummy variables, which will be representing your categories. And that's just how it works. And just important to remember that in that case, that's how you're going to be getting your categories out of the artificial neural network. But let's go back to a simple case of one output value. And now let's, one more point, or kind of like the point that we've already made. I just wanted to reiterate this point. On the left, you've got a single observation. So one row from your data set, and on the right you have a single observation as well, and that is the same observation. So important to remember that, like, whatever inputs you're putting in, that's for one row, and then the output you get, that is for that same exact row. Or if you're training your neural network, then you're putting the inputs in for that one row, you're putting the output in for that one row. So probably, like, if you want to simplify the complexity, think of it as like a simple linear regression or a multivariate linear regression. So you're putting in your values, you have your output. There's no question about it when we're talking about things like regression, because we're so used to it. Same thing here. It's nothing too complex. We're just putting in values, we're getting output, but just remember that every time it's one row you're dealing with, so you don't get confused and start putting in like thinking that these are different rows that you're putting into your artificial neural network or something. This is all just values in that one row. So different observation, different characteristics of or attributes relating to that one observation every single time. Okay, so next thing that we want to talk about here is the synapses. Here we've got synapses, and they all actually get assigned weights. Weights, we're going to talk more about weights further down, but in short, weights are crucial to artificial neural networks functioning, because weights are how neural networks learn. By adjusting the weights, the neural network decides in every single case what signal is important, what signal is not important to a certain neuron, what signal gets passed along and what signal doesn't get passed along, or to what strength, to what extent signals get passed along. So weights are crucial. They are the things that get adjusted through the process of learning. Like when you're training an artificial neural network, you're basically adjusting all of the weights in all of the synapses across this whole neural network. And that's where gradient descent and backpropagation come into play. And those are concepts that we'll also discuss. So basically, those are the weights. That's all we need to know for now. And here we've got the neuron. So signals go into the neuron. And what happens in the neuron? So this is the interesting part. Like, we're talking about the neuron today. What happens inside the neuron? So a few things happen. First thing, and the first step, is that all of these values that it's getting get added up. So it takes the the weighted sum of all of the input values that it's getting. Very simple, right? It's very, very straightforward. Just add up, multiply by the weight, add them up. And then it applies an activation function. Now we're going to talk more about activation functions further down, but it's basically a function that is assigned to this neuron or to this whole layer. And it is applied to this weighted sum. And then from that, the neuron understands if it needs to pass on a signal, if it, that's the signal that it passes on, that the function applied to the weighted sum. But basically, depending on the function, the neuron will either pass on a signal or it won't pass that signal on. And that's exactly what happened here in step 3. The neuron passes on that signal to the next neuron down the line. And that's what we're going to talk about in the next tutorial, because it is quite an important topic. We want to delve deeper into the activation function. But hopefully for now, everything should be pretty clear. How, you've got input values, you've got weights, you've got the synapses, you've got something, happens in the neuron, you've got the weighted sum, and then an activation function applied, and then that is passed down the line. And that is just repeated throughout the whole neural network on and on and on and on. Thousands, hundreds of thousands of times, depending on how many neurons you have, how many synapses you have in your neural network. So there we go. Hope you enjoyed today's tutorial. Can't wait to see you next time. And until then, enjoy deep learning. All right, exciting tutorial ahead. Welcome back to the course on deep learning. Today we're talking about how do neural networks work. Now we've laid a lot of groundwork. We've talked about how neural networks are structured, what elements they consist of, and even their functionality. And today we're going to look at a real example of how a neural network can be applied. And we're actually going to work step by step through the process of its application so we know what's going on. So let's have a look. What example we're going to be talking about? We're going to be looking at property valuation. So we're going to look at a neural network that takes in some parameters about a property and values it. And the thing here, there's a small caveat for today's tutorial, and that is we're not actually going to train the network. So a very important part in neural networks is training them up. And we're going to look at that in the next tutorials in this section. For now, we're going to focus on the actual application. So we're going to work with a neural network that we're going to pretend is already trained up, and that will allow us to focus on the application side of things and not get bogged down in the training aspect. And then we'll cover off the training when we already know the end goal we're working towards. Sound good? All right, let's jump straight into it. So let's say we have some input parameters, right? So let's say we have 4 parameters about the property. We have area in squared feet, we have the number of bedrooms, the distance to the city in miles, the nearest city, and the age of the property. And all of those 4 are going to comprise our input layer. Now, of course, there are probably way more parameters that define the price of a property, but for simplicity's sake, we're going to look at just these 4. Now, in its very basic form, a neural network only has an input layer and an output layer, so no hidden layers. And our output layer is the price that we're predicting. So in this form, what these input variables would do is they would just be weighted up by the synapses, and then the output layer would be calculated, or basically the price would be calculated, and we get a price. And for instance, the price could be calculated as simple as the weighted sum of all of the inputs. And again, here you could use pretty much any function. You could use what we're using now. We could use any of the activation functions we had previously. You could use a logistic regression, you could use a squared function, you could use pretty much anything here. But the point is that you get a certain output. And moreover, most of the machine learning algorithms that exist can be represented in this format. This is basically a diagrammatic representation of how you deal with the variable, right? By changing the weights, the formulas, you can accomplish quite a lot of the machine learning algorithms that we've talked about before, and put them into this form. And that just stands to show how powerful neural networks are, that even without the hidden layers, we already have a representation that works for most other machine learning algorithms. But in neural networks, what we do have is an extra advantage that gives us lots of flexibility and power, which is where that increase in accuracy comes from. And that power is the hidden layers. And there we go. That's our hidden layer. We've added it in. And now we're going to understand how that hidden layer gives us that extra power. And in fact, to do that, we're going to walk through an example. So as we agreed, this neural network has already been trained up. And now we're just going to plug in, we're going to imagine that we're plugging in a property, and we're going to walk step by step through how the neural network will deal with the input variables and calculate the hidden layer and then calculate the output layer. So let's go through this. It's going to be exciting. All right, we've got all 4 variables on the left. And we're going to first start with the top neuron on the hidden layer. Now, as we previously saw in the previous tutorials, all of the neurons from the input layer, they have synapses connecting each one of them to the top neuron in the hidden layer. And those synapses have weights. Now, let's agree that some weights will have a non-zero value, some weights will have a 0 value, because basically not all inputs will be valid, or not all inputs will be important for every single neuron. Sometimes inputs will not be important. And here we can see 2 examples at x1 and x3, the area and the distance to the city in miles are important for that neuron, whereas bedrooms and age are not. And let's think about this for a second. How would that be the case? Why would a certain neuron be linked to the area and the distance? What could that mean? Well, that could mean that normally, the further away you get from the city, the cheaper real estate becomes, and therefore the space in square feet of properties becomes larger, right? So for the same price, you can get a larger property the further away you go from the city. That's normal, right? That makes sense. And probably what this neuron is doing is it is looking specifically, it's like a sniper. It's looking for area properties which are not so far from the city, but have a large area. So for their distance from the city, they have an unfair square foot area, right? So something that's abnormal, it's higher than average. So they're quite close to the city, but they're still large, as opposed to the other ones at the same distance. And so that neuron, again, we're speculating here, but that neuron might be laser picking out those specific properties, and it will activate, and hence the activation function. It'll fire up only when the certain criteria is met, that, the distance and the area of the distance to the city and the area of the property, and it performs its own calculations inside itself, and it combines those two, and as soon as certain criteria is met, it fires up, and that contributes to the price in the output layer. And therefore, this neuron doesn't really care about bedrooms and age of the property, because it's focused on that specific thing. That's where the power of the neural network comes from, because you have many of these neurons, and we'll see just now how the other ones work. But what I wanted to agree here is that let's not even draw these lines for the synapses that are not in play, so that we don't clutter up our image. That's the only reason we're not going to draw them. So let's just get rid of those 2, and that way we will know exactly, okay, so this neuron is focused on area and distance to the city. All right, so as long as we agree on that, let's move on to the next one. Let's take the one in the middle. Here we've got 3 parameters feeding into this neuron. So we've got the area, the bedrooms, and the age of the property. So what could be the reason here? Let's try to understand the intuition, the thinking of this neuron. How is this neuron thinking? Why is it picking these 3 parameters? What could it be? What could have found in the data, right? So we've already established this is a trained up data set. The training has happened a long time ago, maybe like a day ago, or somebody's already trained up this data. So now we're just applying, and we know that this neuron, through all of the thousands of examples of properties, has found out that the area plus the bedrooms plus the age, combination of those parameters, is important. Why could that be the case? Well, for instance, maybe in that specific city, in those suburbs that this neural network has been trained up in, perhaps there's a lot of families with kids, with 2 or more children, who are looking for large properties with lots of bedrooms, but which are new, right? Which are not old properties, because maybe in that area, most of the properties are kind of like big properties are usually old, but there's lots of modern families, and maybe has been a socio-demographic shift, and or maybe there's been like a lot of some growth in terms of employment and jobs for the younger side of population. Maybe just the population demographics have changed, and now younger couples or younger families are looking for properties, but they prefer newer properties. So they want the age of the property to be lower. And hence, from the training that this neural network has undergone, it knows that when there's a property with a large area and with lots of bedrooms, with at least three bedrooms for the parents, for the first child, for the second child, for at least three bedrooms, maybe a guest room, when a new property with a high area and lots of bedrooms, that is valued. That in that market, that is valuable. So that neuron has picked that up. It knows that, okay, so this is what I'm going to be looking for. I don't care about the distance to the city in miles, wherever it is, as long as it has high area, lots of bedrooms. As soon as that criteria is met, the neuron fires up. And the combination of these three parameters, and this is where the power of the neural network is coming from, because it combines these three parameters into a brand new parameter, into a brand new attribute that helps with the evaluation, helps with the valuation of the property. It combines them into a new attribute, and therefore it's more precise. So there we go. That's how that neuron works. And let's look at another one. Let's look at the very bottom one. For instance, this neuron could even have picked up just one parameter. It could have just picked up age and not any of the other ones. And how could that be the case? Well, this is a classic example of when age could mean, like, as we all know, the older property is, usually it's less valuable because it's worn out, probably the building is old, probably, things are falling apart, more maintenance is required. So the price drops in terms of the price of the real estate. Whereas a brand new building, it would be more expensive because it's brand new. But perhaps if a property is over a certain age, that could indicate that it's a historic property. For instance, if a property is under 100 years old, then the older it is, the less valuable it is. But as soon as it jumps over 100 years old, all of a sudden it becomes a historic property, because this is a property where people used to live hundreds of years ago. It tells a story. It's got all this history behind it, and some people like that. Some people value that. In fact, quite a lot of people would like that and would be proud to live in a property, and especially in the higher socioeconomic classes, they would show off to their friends or things like that. And therefore, properties that are over 100 years old could be deemed as historic, and therefore this neuron, as soon as it sees a property over 100 years old, it'll fire up and contribute to the overall price. And otherwise, if it's under 100 years old, then it won't even work. And this is a good example of the rectifier function being applied. So here you've got like a zero until a certain point, and then let's say 100 years old, and then after 100 years old, the older it gets, the higher the value, the higher the contribution of this neuron to the overall price. And it's just a wonderful example of, very simple example of this rectifier function in action. So there we go. That could be this neuron. And moreover, the neural network could have even picked up things that we wouldn't have thought of ourselves, right? For instance, bedrooms plus distance to the city. Maybe that's in combination somehow contributes to the price. Maybe it's not as strong as the other neurons and it contributes, but it still contributes. Or maybe it detracts from the price. That could also be the case. Or other things like that. And maybe a neuron picked up a combination of all four of these parameters. And as you can see, that these neurons, this whole hidden layer situation, allows you to increase the flexibility of your neural network and allows the neural network to look for very specific things. And then in combination, that's where the power comes from. It's like that example of the ants, right? Like an ant by itself cannot build an anthill. But when you have like 1,000 or 100,000 ants, they can build an anthill together, right? And that's the situation here. Each one of these neurons by itself cannot predict the price, but together they have superpowers and they predict the price, and they can do quite an accurate job if trained properly, if set up properly. And that's what this whole course is about, in understanding how to utilize them. There we go. So that is a step-by-step example and walkthrough of how neural networks actually work. I hope you enjoyed today's tutorial, and I can't wait to see you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. All right, today we're talking about the activation function. Let's get straight into it. So this is where we left off previously. We talked about the structure of one neuron. So there it is in the middle. We know that it has some inputs values coming in. It's got some weights. Then it adds up it calculates the weighted sum of those inputs, and then applies the activation function. And on step 3, it passes on the signal to the next neuron. And that's what we're talking about today. We're talking about the value that is going to be passed over. So we're talking about the activation function that's being applied. So what options do we have for the activation function? Well, we're going to look at 4 different types of activation functions that you can choose from. Of course, there are more different types of activation functions, but these are the predominant ones that you'll be hearing about and that we'll be using in this course. So here is the threshold function. This is what it looks like. So on the x-axis, you have the weighted sum of inputs. On the y-axis, you have just the values from 0 to 1. And basically, the threshold function is a very simple type of function where if the value is less than 0, then the threshold function passes on 0. If the value is more than 0 or equal to 0, then threshold function passes on a 1. So it's basically kind of like a yes-no type of function, very, very straightforward, very kind of like rigid type of function, either yes or no, no other options. So there you go, that's how it works. Very simple function. Let's move on to something a bit more complex now. The sigmoid function, very interesting formula that we have here. You'll see just now. There it is, 1 divided by 1 plus e to the power of minus x. Whereas in this case, of course, x is the value of the summed, of the weighted sums. And so this is what the sigmoid looks like. It's a function which is used in the logistic regression, if you recall from the machine learning course. So what is good about this function is that it is smooth. Unlike the threshold function, this one doesn't have those kinks in its curve, and therefore it's just nice and smooth, gradual progression. So anything below 0, it just like drops off. Above 0, it approximates towards 1. And this sigmoid function is very useful in the final layer, in the output layer, especially when you're trying to predict probabilities, and we'll see that throughout this course. And then we've got the rectifier function. Rectifier function, even though it has a kink, is one of the most popular functions for artificial neural networks. So it goes all the way to 0. It is 0, and then from there, it gradually progresses as the input value increases as well. And we'll see that throughout the course. We'll see that in other intuition tutorials, and we'll also see that how we use this function in the practical side of the course. And I will comment on this a bit more in a few slides from now. So just remember that a rectifier function is one of the most used functions in artificial neural networks. And finally, we've got one more function that you will probably hear about. It's the hyperbolic tangent function. It's very similar to the sigmoid function, but here the hyperbolic tangent function goes below 0. So the values go from 0 to 1, or approximate to 1, and go from 0 to minus 1 on the other side. And that can be useful in some applications. So we're not going to go into too much depth on each one of these functions. I just wanted to acquaint you with them so that you know what they look like and what they're called. If you'd like to get some additional reading, then check out this paper by Javier Glorot, called Deep Sparse Rectifier Neural Networks, 2011 paper. And there you will find out exactly why the rectifier function is such a valuable function, why it's so popularly used. But nevertheless, for now, you don't really need to know all of those things. For now, we're just going to start applying them. We're going to start using them more and more and more. And so when you feel comfortable with the practical side of things, then you can go and refer to this paper, and then you will be able to soak in that knowledge much quicker, and it'll make much more sense. So, but just keep this in mind that when you're ready, when you feel that you're ready, then you can go and refer to this paper and get some valuable knowledge from there. So just to quickly recap, we have the threshold activation function, which looks like this, the sigmoid activation function, which looks like this, we have the rectifier function, and we have the hyperbolic tangent function. And now to finish off this tutorial, let's quickly do a few exercises. So we'll just do 2 quick exercises to help that knowledge sink in. So first one is, we've got an example here of a neural network with just one neuron and then right away the output layer. And the question is, assuming that your dependent variable is binary, so it's either 0 or 1, which threshold function would you use? So out of the ones that we've discussed, we have the threshold function, the sigmoid function, the rectifier function, and we've got the hyperbolic tangent function. in their raw forms, which ones would you be able to use for a binary variable? Okay, so the answers here are, there's two options that we can approach this with. So number one is the threshold activation function. Because we know that it's between 0 and 1, and it gives you a 0 under certain values, and then otherwise it gives you a 1, so it only can give you two values. It fits perfectly, fits this requirement perfectly, and therefore you can just say y equals the threshold function of your weighted sum, and that's it. And in the second case, what you could use is the sigmoid activation function. It is actually also between 0 and 1, just what we need, but at the same time, you want it's just 0 or 1, right? So it's not exactly what we need, but in this case, what you could use it as is the probability of y being yes or no. So we want y to be 0 or 1, but instead we'll say that the sigmoid function, sigmoid activation function, tells us whether it tells us the probability of y being equal to 1. So basically, the closer you get to the top, the more likely it is that this is indeed a 1 or a yes rather than a no. And yeah, so that's very similar to the logistic regression approach. And those are just two examples of if you have a binary variable. And now let's have a look at another practical application. Let's have a look at how all this would play out if we had a neural network like this. So in the first input layer, we have some inputs. They are sent off to our first hidden layer, and then an activation function is applied. And usually what you would apply here, and what you'll see throughout this course, is we would apply a rectifier activation function. So it would look something like that. We apply the rectifier activation function, and then from there, the signals would be passed on to the output layer, where the sigmoid activation function would be applied, and that would be our final output, and that could predict a probability, for instance. So this combination is going to be quite common, where in the hidden layers we apply the rectifier function, and then in the output layer we apply the sigmoid function. So there we go. Hope you enjoyed today's tutorial. Now you are quite well versed in the 4 different types of activation functions, and you will get some hands-on practical experience with them throughout this course. We'll be using them all over the place, so you'll get to know them quite intimately, and you should be quite comfortable with them. But for now, this is the knowledge that you need to progress and understand what is going to be happening further down in this course. And on that note, I will look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. In today's tutorial, we're talking about gradient descent. What we learned previously was that in order for a neural network to learn, what needs to happen is backpropagation. And that is when the error, the difference or the sum of squared differences between y hat and y is backpropagated through the neural network, and the weights are adjusted accordingly. So we saw that, and today we're going to learn exactly how these weights are adjusted. So let's have a look. This is our very simple version of a neural network, a perceptron or a single layer feed-forward neural network. And what we can see here is this whole process in action, where we've got some input value, then we've got a weight, then a activation function is applied, we get y hat, and then we compare it to the actual value, we calculate the cost function. So how can we minimize the cost function? What can we do about it? Well, one approach to do it is a brute force approach, where we just take lots of different possible weights and look at them and see which one works best. And what we would do is, for instance, we'd try out, for let's say, for example, 1,000 weights, and we'd try them out. We'd get something like this for the cost function, and this is a chart of on the y-axis you have cost function, on the vertical axis, on the horizontal axis you have y hat, and because you can see the formula is y hat minus y squared, this is what the cost function would look, something like that. And basically you'd find the best one is over here. So very simple, very intuitive approach. Why not do this brute force method? Why not just try out 1,000 different 1,000 different parameters or inputs for weights and see which one works the best. You'll find the best one that way. Well, if you have just one weight to optimize, this might work. But as you increase the number of weights, increase the number of synapses in your network, you have to face the curse of dimensionality. And so what is the curse of dimensionality? The best way to describe this or explain it is to just look at a practical example. So remember this example we had when we were talking about how neural networks actually work, where we were building or running a neural network for property evaluation. So this is what it looked like when it was trained up already. Well, when it's not trained, before it's trained, before we know what are the weights, the actual neural network looks like this, right? Because we have all these different possible synapses, and we still have to train up the weights. And here we have a total of 25 weights. So 4 times 5 at the start, plus 5 more from the hidden layer to the output layer, 25 weights total. And let's see how we could possibly brute force 25 weights. It's a very simple neural network right here. Very simple, just one hidden layer. And how could we brute force our way through a neural network of this size? Well, let's do some simple mathematical calculations. We have 25 weights, so that means if we have 1,000 combinations that we're going to test out for every weight, the total number of combinations is 1,000 to the power of 25 or 1,000 or 10 to the power of 75 different combinations. Now let's see how Sunway Taihu Lite, the world's fastest supercomputer as of June 2016, how would it approach this problem, right? So Sunway Taihu Lite, it looks like this. It's a whole huge building pretty much for this one supercomputer, and it got the Guinness World Record for being the fastest supercomputer. Right now it is the fastest supercomputer in the world, and Sunway Taihu Lite can operate at a speed of 93 petaflops. A flop stands for floating operation per second. So it can do 93 to the power times 10 to the power of 15 floating operations per second. That's how quick it is. In comparison, average computers right now, they do like just over several gigaflops and so on. So like kind of those ranges, way less than Sunway Taihu Lite. So Sunway Taihu Lite is in the forefront of technology. And let's say hypothetically that it can do test one combination for our neural network in one flop, basically in one floating operation. That is not possible. That is not practical because you need multiple floating operations to test out a single weight in your neural network. But even let's give it a head start. Let's say that it can do that in a ideal world. It can do that in one floating operation. It can do one test per one floating operation. That means it will still require 10 to the power of 75 divided by 93 times 10 to the power of 15 seconds to run all of those tests, to brute force through that network. So that means approximately 10 to the power of 58 seconds. And that is the same as 10 to the power of 50 years. That is a huge number. That is longer than the universe has existed. And that is definitely not going to, this number is so huge, it's just definitely not going to work for us at all in our optimization. So there we go. This is a no-no even on the world's fastest supercomputer, Sunway Taihu Lite. So we have to come up with a different approach. How are we going to find the optimal weight? By the way, our neural network was very simple. What about if the neural network looks like something like this, right? Or even greater than that? Then, yeah, it's just not going to happen at all, ever. So the method we're going to be looking at is called gradient descent, and you may have heard of it already. If not, we will find out what it is right now. So there's our cost function, and now we're going to see how we can come up with a faster way to find the best option. So let's say we start somewhere. You got to start somewhere. So we start over there, and from that point in the top left, what we're going to do is we're going to look at the angle of our cost function at that point. So we're just going to basically, that's why it's called gradient, because you have to differentiate. We're not going to look at the mathematical equations. We will provide some tips on additional reading at the end of the next lecture. But basically, you just need to differentiate, find out what the slope is in that specific point, and find out if the slope is positive or negative. If the slope is negative, like in this case, means that you're going downhill. So to the right is downhill, to the left is uphill. And from there, it means you need to go right. Basically, you need to go downhill. And that's what we're going to do. Vroom. Takes a step, right? The ball rolls down. Again, same thing. You calculate the slope. This time the slope is positive, meaning right is uphill, left is downhill, and you need to go left. And you roll the ball down. And again, you calculate the slope, and you roll the ball right. There we go. So that's how you find, in simple terms, that's how you find the best weights, the best situation that minimizes your cost function. Of course, it's not going to be like a ball rolling is going to be a very zigzaggy type of approach, but it's easier to remember, or kind of it's more fun to look at it as a ball rolling. But in reality, yes, you just it is going to be like a step-by-step approach, so it's going to be a zigzaggy type of method. Yeah, and also there's lots of other elements to it. There's things like, for instance, why does it go down? Why does it not like go away over the line? So it could have jumped out of this, gone upwards instead of downwards, and things like that. So there are parameters that you can tweak, and again, we will mention where you can find out more on that, and plus we'll have this in the practical application. But in the simplest intuitive approach, this is what is happening. We are getting to the bottom by just understanding which way we need to go. Instead of brute forcing through thousands and thousands and millions and billions and quadrillions of combinations, we can just simply every time have a look at which way is it sloping. So right, like you imagine you're standing on a hill, which way does it feel that it's going downwards? And whichever way it is going downwards, you just keep walking that way. You take 50 steps that way, and then you assess again. Okay, which way is it going downwards? This way. Okay, now take 50 steps or less. Take 40 steps that way. So it gets less and less and less as you get closer. So here's an example of gradient descent applied in a two-dimensional space. So that was a one-dimensional example. Here we have a two-dimensional space for the gradient descent. As you can see, it's getting closer to the minimum. And it's also called gradient descent because you're descending into the minimum of the cost function. And finally, here's a gradient descent applied in 3 dimensions. This is what it looks like if you project it onto 2 dimensions. You can see it's zigzagging its way into the minimum. So there we go. That was gradient descent. In the next tutorial, we'll talk about stochastic gradient descent. It'll be a continuation of this tutorial. And I look forward to seeing you there. Until next time, enjoy deep learning. Hello and welcome back to the course on deep learning. Now that we've seen neural networks in action, it's time for us to find out how they learn. So let's dive straight into it. There are 2 fundamentally different approaches to getting a program to do what you want it to do. One is hard-coded coding, where you actually tell the program specific rules and what outcomes you want, and you just guide it throughout the whole way, and you account for all the possible options that the program has to deal with. On the other hand, you have neural networks where you create a facility for the program to be able to understand what it needs to do on its own. So you basically create this neural network where you provide it inputs, you tell it what you want as outputs, and then you let it figure everything out on its own. 2 fundamentally different approaches, and that is something to keep in mind as we go through these tutorials. Our goal is to create this network which then learns on its own. We're going to avoid trying to put in the rules. And a good example that I can give you right now is, this will come further in the course, but it's just a very visual example. For instance, how do you distinguish between a dog and a cat? On the left side, on the approach that's depicted on the left, you would program things in like the cat's ears have to be like this. Look out for whiskers. Look out for this type of nose. Look out for this type of shape of face. Look out for these colors. You describe all of these things, and you'd have conditions like if the ears are pointy, then cat. If the ears are sloping down, then possibly dog, and so on. On the other hand, for a neural network, you just code the neural network, so you code the architecture, and then you point the neural network at a folder with all these cats and dogs, with images of cats and dogs, which are already categorized, and you tell it, okay, I've got some images of cats and dogs, go and learn what a cat is, go and learn what a dog is, and the neural network will on its own understand everything it needs to understand. And then further down, once it's trained up, when you give it a new image of a cat or a dog, it'll be able to understand what it was. So there they are. Those are the two fundamentally different approaches. And today we're going to slowly start getting into how that second approach works. All right, so let's get straight to it. Here we have a very basic neural network with a one layer. This is called a single layer feed-forward neural network, and it is also called a perceptron. Now, before we proceed, one thing that we do need to adjust is that output value. Right now, you can see that it's just a Y. We need to put a Y hat in there, and the reason for that is usually Y stands for the actual value, and that's what we're going to be using. So Y is going to be the actual value, which we see in reality. Output value is the predicted value by the algorithm, by the neural network. Y hat is the output value, basically. That's the denomination for the output value. And the perceptron was first invented in 1957 by Frank Rosenblatt. And his whole idea was to create something that can actually learn and adjust itself. And this is what we're going to be looking at now. So we've got our perceptron. Let's see how our perceptron learns. So let's say we have some input values that have been supplied to the perceptron or basically to our neural network. Then the activation function is applied. We have an output. And now we're going to plot the output on a chart. So there it is, our output Y hat. Now, what we need to do is, in order to be able to learn, we need to compare the output value to the actual value that we want the neural network to get, right? And that is the value Y. And so if we plot it here, you'll see that there's a bit of a difference. Now we're going to calculate a function called the cost function. It's calculated as 1/2 of the difference, of the squared difference between the actual value and the output value. Now, there are many ways you can come up with a cost function. There are many different cost functions that you can use. This is probably the most commonly used cost function, and why it is specifically this function that we use, we'll find out further down when we're talking about gradient descent. But for now, we're just going to agree that this is the cost function. And basically what the cost function is telling us is what is the error that you have in your prediction. And our goal is to minimize the cost function, because the lower the cost function, the closer the Y hat is to Y. Okay, so as long as we agree on that, let's proceed. So basically from here, what happens is there's our cost function. And from here, what happens is now we're going to, once we've compared, now we're going to feed this information back into the neural network. So there we go. There's the information going back into the neural network, and it goes to the weights, and the weights get updated. Basically, the only thing that we have control of in this very simple neural network are the weights, W1, W2, all the way to Wm. And our goal is to minimize the cost function, so all we can do is update the weights. So we update the weights, tweak them a little bit, and how exactly we'll find out further down. But for now, we agree that we update the weights, and then we continue. So, but here I've put up this screenshot of the data just to make one point very clear, that right now, throughout this whole experiment, everything we're doing right now, we're dealing with just the one row. So we have a data set of one row where we have, for instance, we're dealing with how long you study, like the variable that we're predicting is what results you're going to get on an exam, and the independent variables that we have is how many hours did you study for, how many hours did you sleep, and what did you get on the quiz in the mid-semester. So in the middle of the semester, there's a quiz, what percentage did you get there? So based on those variables, we're trying to predict what score you'll get for the exam. And in exam, the 93%, that's the actual value. So that's y. So we feed these three values into our neural network again for the second time now. And then we're going to be comparing the result to y. So let's see how this works. We feed these values into the neural network, everything gets adjusted, and weights get adjusted. So as you can see, let's do this again. We're going to feed the values. Again, the point here is that we're feeding in these same values. So we only have one row. We're training on one row. This is because this is just a very simple, basic example. Then we'll see what happens when there's more rows. So again, we feed these rows in. Our cost functions get adjusted. As you can see, everything happens along those lines again. So as you can see, every time our y hat is changing because we've tweaked the weights, our y hat is changing, our cost function is changing. Let's have a look again. So we feed those in, y hat is changing, cost function is changing. We get information back, feed back to the weights so that the weights get adjusted again. We feed in the same values every time. Everything gets adjusted, goes back to the weights. And one more time, feed in, okay. And another time, so we've adjusted the weights, we feed in the information, and there we go. So now this time the y hat is equal to y, cost function is 0. Usually you won't get cost function equal to 0, but this is a very simple example. So hopefully all that made sense. Every time we feed in exactly that same row, because just in this case we're just dealing with that one row, into our neural network, where then the values get multiplied by the weights, the activation function is applied, we get y hat is compared to y, then we see how the cost function has changed, feed that information back into the neural network, and adjust the weights again. And then we repeat the same process again with the same exact row. We're trying to minimize that cost function. So up until now, we've been dealing with just that one row. Let's see what happens when you have multiple rows. So here's the full data set. We have 8 rows of how many hours you slept, or maybe these are different students taking the same exam, how many hours they studied, how many hours they slept before the exam, what they got on the quiz, and their final result on the test. And as you can see here on the left, I've got 8 of these perceptrons. Actually, they are all the same perceptron, so this is also important to understand. I just multiplied it or like duplicated 8 times just so that we can conceptually understand. But the important thing here is the same neural network. We're going to be feeding these into the one same neural network. So let's get started. So one epoch, as you'll hear Hadlan mentioning, one epoch is when we go through a whole data set and we train our neural network on all of these rows. So let's get started. So there's our first row, and there's y hat for the first row. There's the second row, there's y hat for the second row. So again, it's being fed into the same neural network every time. I've just copied them several times so we can visually see how this is happening. Then again, it's happening again. That's third row, fourth row. There's our y hat for the fourth row, and so on. Basically, then we get the same values for the remaining 4 rows as well. So every time we just feed in a row into our neural network, we get a value. Then we compare to the actual values. So there are the actual values. So for every single row, we have an actual value. And now, based on all of these differences between y hat and y, we can calculate the cost function, which is the sum of all of those squared differences between y hat and y, and all of that is halved. And there's our cost function. And basically now what we do after we have the full cost function, we go back and we update the weights. We update W1, W2, W3. And the important thing to remember here is that all of these perceptrons, all of these neural networks is actually one neural network. So there's not 8 of them, there's just one. And when we update the weights, we're going to update the weights in that one neural network. So basically the weights are going to be the same for all of the rows. So it's not the case that every row has its own weights. No, all of the rows share the weights. And so that's why we looked at the cost function, which is the sum of the squared differences. And then we updated the weights. And now from here, that was just one iteration. Next, we're going to run this whole thing again. We're going to feed every single row into the neural network, find out our cost function, and do this whole process again. So just as we saw previously, where we had just one row and we were doing everything again and again and again, same thing here, but now we're going to be doing it with 8 rows or 800 rows or 8,000 rows, however many rows you have in your data set. You do this process and then you calculate the cost function. And the goal here is to minimize the cost function and to get, as soon as you've found the minimum of the cost function, that is your final neural network. That means your weights have been adjusted and you have found the optimal weights for this data set that you're training on, and you're ready to proceed to the testing phase or to the application phase. And this whole process is called backpropagation. So some additional reading that you might want to do for the cost function, and I know we just talked about one, and there are many different ones. A good article is located on Cross-Validated. It's called A List of Cost Functions Used in Neural Networks Alongside Applications. So the URL is there, but you can just Google for that exact search term or search phrase, and this one will be the first one that pops up. It's actually got some good examples and application or use cases for different cost functions. So if you're interested to learn more about cost functions, check out this article. And on that note, I hope you enjoyed today's tutorial. I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about stochastic gradient descent. Previously, we learned about gradient descent, and we found out that it is a very efficient method to solve our optimization problem where we're trying to minimize the cost function. It basically takes us from 10 to the power of 57 years to solving a problem within minutes or hours or within a day or so. And it really helps speed things up because we can see which way is downhill and we can just go in that direction and take steps and get to the minimum faster. But the thing with gradient descent is that this method requires for the cost function to be convex. And as you can see here, we've specifically chosen a convex cost function. Basically, convex means that the function looks similar to what we are seeing now, that it's just convexed into one direction, and that it in essence has one global minimum, and that's the one that we're going to find. But what if our function is not convex? What if our cost function is not convex? What if it looks something like this? Well, first of all, how could that happen? Well, that could happen because if we, first of all, choose a cost function which is not the square difference between y hat and y, or if we do choose the cost function which is like that, but then in a multidimensional space it can actually turn into something that is not convex. And so what would happen in this case if we just try to apply our normal gradient descent method? Something like this could happen. We could find a local minimum of the cost function rather than the global one. So this one was the best one and we found the wrong one, and therefore we don't have the correct weights. We don't have an optimized neural network. We have a subpar neural network. And so what do we do in this case? Well, the answer here is stochastic gradient descent. And it turns out the stochastic gradient descent doesn't require for the cost function to be convex. So let's have a look at the two differences between the normal gradient descent that we talked about and the stochastic gradient descent. So normal gradient descent is when we take all of our rows, we plug them into our neural network. And once again, here we've got the neural network copied over several times, but the rows are being plugged into that same neural network every time. So there's only one neural network. This is just for visualization purposes. And then once we've plugged them in, we've calculated our cost function based on the formula on the right and looking at the chart at the bottom. And then we adjust the weights then. And this is called the gradient descent method, or it's also the proper term is the batch gradient descent method. So we take the whole batch of from our sample, we apply it, and then we run that. The stochastic gradient descent method is a bit different. Here we take the rows one by one. So we take this row, we run our neural network, and then we adjust the weights. Then we move on to the second row. We take the second row, we run our neural network, we look at the cost function, and then we adjust the weights again. And then we take another row, take row 3, We run our neural network, we look at the cost function, we adjust the weight. So basically, we're looking at we're adjusting the weights after every single row rather than doing everything together and then adjusting weights. Two different approaches, and now we're going to just compare the two side by side. So here they are. This is how to visually remember them. So you've got the batch gradient descent where you're adjusting the weights after you've run them, after you've run all of the rows in your neural network. And then basically you adjust the weights and you run the whole thing again, iteration, iteration, iteration. In the stochastic gradient descent method, you run one row at a time and you adjust the weights, you adjust the weights, you adjust the weights, and then you do everything again and again. And that is called the stochastic gradient descent method. The main two differences are that the stochastic gradient descent method helps you avoid the problem where you find those local extremos or local minimums rather than the overall global minimum. And the reason for that, in simple terms, is that the SGD, or the stochastic gradient descent method, has much higher fluctuations because it can afford them. It's doing one iteration or one row at a time, and therefore the fluctuations are much higher, and it is much more likely to find the global minimum rather than just the local minimum. And the other thing about the stochastic gradient descent method compared to the batch gradient is it's faster. Like, the first impression that you might have is because it's doing every single row one at a time, it's slower, but actually, in fact, it is faster because it doesn't have to load up all the data into memory and run and wait until all of those rows are run all together. It can just run them one by one, so it's a much lighter algorithm. It's much faster in that sense. So though it has way more, in those senses, it has more advantages over the batch gradient descent method. The main advantage of, or the main kind of like pro for the batch gradient descent method is that it is a deterministic algorithm rather than stochastic gradient descent being a stochastic algorithm, meaning it's random. And with the batch gradient descent method, as long as you have the same starting weights for your neural network, every time you run the batch gradient descent method, you will get the same iterations, the same results for your for the way your weights are being updated. For the stochastic gradient descent method, you won't get that because it is a stochastic method. You're picking your rows possibly at random, and you are updating your neural network in a stochastic manner, and therefore you're just going to, every single time you run the stochastic gradient descent method, even if you have the same weights at the start, you're going to have a different process, different iterations to get there. So that's in a nutshell what stochastic gradient descent is. Also, there's a method in between the two called the mini batch gradient descent method, where you combine the two and you basically run, rather than running a whole batch or running one at a time, you run batches of rows, maybe 5, 10, 100, however many rows you decide to set. You run that number of rows at a time, then you update your weights, then you update your weights, and so on. And that's called the mini batch gradient descent method. If you'd like to learn more about gradient descent, there's a great article which you can have a look at. It's called A Neural Network in 13 Lies of Python, Part 2, Gradient Descent by Andrew Trask. And the link is below. It's on GitHub, 2015 article. Very well written, in very simple terms. It's got some interesting philosophical or just interesting thoughts on how to apply gradient descent, what are the advantages and disadvantages, and how to do things in certain situations. So it's got some very cool tips, tricks, and hacks. Very easy read, so definitely check that out. And another one, a bit more heavier read for those of you who are into mathematics, who want to get to the bottom of the mathematics, why gradient descent in that specific, what are the formulas that are driving gradient descent, how is it calculated, and so on. Check out the article, or actually the book. It's a free online book called Neural Networks and Deep Learning by Michael Nielsen, 2015 book. It's just basically, it's all online. You can go ahead and check it out there. And they're, again, very soft introduction to the mathematics, but the mathematics are pretty heavy as you go along, as you read through the article. But at the same time, it gets you into that mood. I think even it has like a warm up chapter where you first warm up with the math and then you jump into them. So interested in math, then this is the article to go to. And there we go. So that's in a nutshell the difference between gradient descent and stochastic gradient descent, and how the two work. And on that note, we're going to wrap up today's tutorial. I look forward to seeing you on the next one. And until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're going to wrap up with backpropagation. All right, so we already know pretty much everything we need to know about what happens in the neural network. We know that there's a process called forward propagation where information is entered into the input layer and then it's propagated forward to get our y-hats, our output values, and then we compare those to the actual values that we have in our training set, and then we calculate the errors. Then the errors are back propagated through the network in the opposite direction, and that allows us to train the network by adjusting the weights. So the one key important thing to remember here is that backpropagation is an advanced algorithm driven by very interesting and sophisticated mathematics, which allows us to adjust the weights, all of them at the same time. All of the weights are adjusted simultaneously. So if we were doing this manually, or if we were coming up with a different type of algorithm, then even if we calculated the error and then we were trying to understand what effect each of the weights has on the error, we'd have to somehow adjust each of the weights independently or individually. The huge advantage of backpropagation, and this is a key thing to remember, is that during the process of backpropagation, simply because of the way the algorithm is structured, you are able to adjust all of the weights at the same time. So you basically know which part of the error each of your weights in the neural network is responsible for. Now, that is the key fundamental underlying principle of backpropagation, and this was why it picked up so rapidly in the 1980s, and this was a major breakthrough. And if you'd like to learn more about that and how exactly the mathematics works in the background, then a good article, which we've already mentioned, is the Neural Networks and Deep Learning. It's actually a book by Michael Nielsen. There you'll find the mathematics written out, and it'll help you understand how exactly this is possible. But for now, for our purposes, if from an intuition point of view, the important part is to remember that that's what backpropagation does. It adjusts all of the weights at the same time. And now we're going to just wrap everything up with a step-by-step walkthrough of what happens in the training of a neural network. All right, so step one, we randomly initialize the weights to small numbers close to 0 but not 0. We didn't really focus on the initialization of weights during the intuition tutorials, but the weights have to start somewhere, and they are initialized with random values near 0, and from there, through the process of forward propagation, back propagation, these weights are adjusted until the error is minimized, until the cost function is minimized. Then step two, input the first observation of your data set, so the first row, into the input layer. Each feature is one input node. So basically take the columns and put them into the input nodes. Step three, forward propagation. From left to right, the neurons are activated in a way that the impact of each neuron's activation is limited by the weights. So the weights basically determine how important each neuron's activation is. Then propagate the activations until getting the predicted result, y hat in this case. So basically you propagate from left to right, you go all the way until you get to the end and you get your y hat. Then compare the predicted result to the actual result, measure the generated error. And then you do the backpropagation. From right to left, the error is backpropagated. Update the weights according to how much they're responsible for the error. Again, you are able to calculate that because of the way the backpropagation algorithm is structured. The learning rate decides by how much we update the weights. Learning rate is a parameter you can control in your neural network. Step 6, repeat steps 1 to 5 and update the weights after each observation. That is called reinforcement learning, and in our case that was stochastic gradient descent, or repeat steps 1 to 5, but update weights only after a batch of observations. So batch learning, it's either full gradient descent or batch gradient descent or mini batch gradient descent. And step 7, when the whole training set passed through the artificial neural network, that makes an epoch, redo more epochs. So basically you just keep doing that and doing that and doing that until allowing your neural network to train better and better and better and constantly adjust itself as you minimize the cost function. So there we go. Those are the steps you need to take to build your artificial neural networks and train it. And these are the steps that you will be taking together with Hadelin in the practical tutorials. Wish you the best of luck, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're kicking off convolutional neural networks. This is going to be exciting. Let's dive straight into it. We're going to start off with an image. What do you see when you look at this image? Do you see a person looking at you, or do you see a person looking to the right? You can see that your brain is struggling to adjust. If you look to the right side of the image, just look at the right border of the image, you'll see a person looking to the right. If you look at the left border of the image, you'll see a person looking at you. And this just proves that what our brain is looking for when we see things is features. Depending on the features that it sees, depending on the features that you process, you categorize things in certain ways. So when you look on the right side of the image, you see certain features of a person looking to the right because they're closer to your center of focus. And therefore, your brain classifies it as a person looking to the right. When you look to the left side of the image, you see more features of a person looking at you. And therefore, your brain classifies it as such. So let's have a look at another one. This is a very famous image. You probably have already seen it, but what do you see here? So some people will say that they see a young lady wearing a dress looking away. Some people will say they see an old lady wearing a scarf on her head looking down. So I'm going to point these features out and you'll see that it'll become very obvious. So this is the face of the young lady looking away. She's looking into the distance. That's her coat, that's her hair, that's her little feather in her hair. And on the other hand, this is the head of the old lady looking down. That's her nose, that's her mouth, that's her chin, that's the scarf on her head, and she's looking down. So as you can see, 2 in 1, and depending on which features your brain picks up, it will switch between classifying the image as one or the other. The oldest one of these illusions recorded in the printed work is this one. It's the duck or the rabbit. So is this a duck or is this a rabbit? Another example. And now I'm going to show you an image which will just, for a second, just look at it and see what emotions or what kind of experience, visual experience you go through. So what do you see? Do you feel like a bit, not dizzy, but a bit dazzled? Like your brain is trying to understand what it is. Like it's jumping between her eyes, the up and down eyes. And this is a classic example of when there are certain features where it could be this, it could be that, but your brain cannot decide. And because both seem plausible. And yeah, so basically all these examples illustrate to us how the brain works, that it processes certain features on an image or on whatever you see in real life, and it classifies that as such. And you've probably been in situations when you look over your shoulder quickly and you see something, you think it's, I don't know, if it's like a ball, but it turns out to be a cat, or you think it's a car, but it turns out to be a shadow, and things like that. That's because you don't have enough time to process those features, or you don't have enough features to classify things as such. And this is, for me, this is very interesting, because what we're going to be doing with neural networks, with convolutional neural networks, is very similar, and you'll find that the way that computers are going to be processing images is going to be extremely similar to the way we are processing images. So it's very valuable to understand and just kind of remember these things, that this is how we do it. And I'm going to take this lady off your screens because she's probably already freaking you out by now. So here's something different. Here's an experiment. An experiment done on computers, on convolutional neural networks. So we're slowly moving now from humans to computers. And this slide is from a talk by Geoffrey Hinton. And here you have, basically it describes an experiment that he had done on some convolutional neural networks that he had trained up. So here you see 3 images, and we're going to go through them left to right and see how you would classify them, and then see how the computer classified them. So on the left, what do you think this is? You probably said cheetah, and you will be right, and this is what the computer said. So, and right away, right off the bat, we're going to learn how to read these images, because if you're going to go deep into convolutional neural networks, no pun intended, if you're going to start learning more and more about them and using them, you'll see a lot of these. So, and I've actually seen people read them incorrectly. So here at the top, cheetah is what it actually is. So that's the actual correct label of the image. That's what the label of the image is, regardless of any processing and computer vision. And then here are the guesses, the top 4 or 5 sometimes guesses of the algorithm, and they're given the probability. So the computer said, or the neural network said, cheetah, leopard, snow leopard, or Egyptian cat can be one of the 4, and cheetah has the highest vote. And throughout this part of the course, you will understand what these votes mean and how they are derived. But for now, it's pretty intuitive, right? So it's a cheetah in reality, and the neural network guessed right. It said with a high probability, about like 95, 99%, it's a cheetah. Then the second one, what do you think that is? That is a bullet train. And the neural network was able to distinguish between bullet train, passenger car, subway train, electric locomotive. Those are the top choices. Of course, it had many more options. These neural networks learn to distinguish from not just 4 categories, from dozens, thousands of categories at the same time. So those are the 4 options that it picked. And so that's bullet train, and it's bullet train. So what do you think the last one is? There are a couple of options, right? It's not very clear what it is. It could be a frying pan, it could be a magnifying glass, it could be even maybe a pair of scissors, some might say. Well, the neural network said it was a pair of scissors. But you can see how you can go wrong here. First of all, it's not a very clear image, and also you can see that the probabilities are not as clear here. So the neural network was a bit confused, a bit indecisive, just as we are. So it said scissors with the highest probability, but then it had hand glass, which it actually was, with not so far away on second place, and frying pan, stethoscope. So basically, here you can see that scissors was its first guess, but the correct option was number 2, and that's why it's highlighted in red. So there we go. That's what neural networks are already capable of, and this is actually quite an old slide. This was several years ago. Now they're even better, and you will see that from the practical application that you will be coding together with Hadoop. But now let's try to understand a bit better what convnets, or convolutional neural networks, actually are, and why are they gaining so much popularity. And they actually are gaining popularity. So you can see here a Google Trends comparison I did just yesterday. Here you can see that convolutional neural networks are even taking over artificial neural networks. So a massive increase, and they're just going to keep going that way, because it is a very important field. That is where all the things happen, such as like self-driving cars. How do they recognize people on the road? How to recognize stop signs and things like that? How is Facebook able to tag images or people in images? And not only just like, remember previously, years ago, you had to tag people yourself, then it would recognize faces, you had to add the names, and now it just recognizes the faces and adds the names at the same time. Well, that is what convolutional neural networks are capable of. And speaking of Facebook, if Geoffrey Hinton is the godfather of artificial neural networks and deep learning, then Yann LeCun is the grandfather of convolutional neural networks. Yann LeCun is a student of Geoffrey Hinton's, and in fact, here you can see them together. And Geoffrey Hinton now is pioneering deep learning at Google. Yann LeCun is the director of Facebook Artificial Intelligence Research and also a professor at NYU. So slowly I love this part of the course. Slowly we're building up this these names, or this kind of picture of the profiles of the people who are driving this field. And in the next couple of parts, we'll get to know about a few more, and we'll have this whole mafia, as they call themselves, or Jan LeCun calls them, mafia or conspiracy of deep learning, and you'll learn a bit more about how this whole field developed. And these are just some great people. And so Jan LeCun, back in the 80s and the 90s, made significant contributions to the field of convolutional neural networks, and as we'll see throughout this course, has been able to develop or help the world develop something so extremely powerful. So moving on to how convolutional neural networks work. You have an input. It's very simple. It's very straightforward. So you have an input image. It goes through the convolutional neural network, and you have an output label. So it classifies that image as something like as a cheetah or a bullet train or something else. Now, kind of like going into a bit more detail, for instance, you can, after a neural network has been trained up on certain images, on certain classified images or categorized images that have been categorized prior, after that you can give it, let's say a neural network has been trained up to recognize facial expressions, emotions. You can give it a face of a smiling person. It's not just a face like a drawing of a face like this, but actual face of a person smiling, and it will tell you that that person is happy. And you can give it a face of a person that's frowning. It will tell you that that person is sad. It can recognize these emotions, and as you can see, that's already very powerful in terms of so many different applications just of this one example you can think of right away. And in both cases, it will give you a probability. So it won't say, with 100% the person's happy or sad. It'll be 99 or 98 or maybe 80% when it's unclear of what's going on. And just like we are, right? Sometimes we can mistake things for what they're not, or sometimes we can sometimes it's just not clear if the person is smiling or frowning, or if it's a dog or a cat, or if it's a train or a bullet train, right? Sometimes we haven't seen enough features, and it all goes down to features, because that's how we process visual information, as we saw from the start of this tutorial. So, but how is a neural network able to recognize these features? Well, it all starts at the very basic level. Let's say you have an image. You have two images. One is a black and white image of 2 by 2 pixels, and one is a colored image of 2 by 2 pixels. Well, neural networks leverage the fact that the black and white image is a two-dimensional array. So the way we see it right now on the left is just the visual representation, right? So it's some kind of picture, and for simplicity's sake, it's just a 2 by 2 picture. But in computer terms, it's actually a two-dimensional array with every single one of those pixels having a value between 0 and 255. So that's eight bits of information. 2 to the power of 8 is 256. So therefore, the values are from 0 to 255, and that's the intensity of the color. And in this case, the color white. So 0 will be a completely black pixel, 255 will be a completely white pixel, and between them you have the grayscale range of possible options for this pixel. And based on that information, computers are able to then work with the image. And that's kind of like the starting point, that any image has a digital representation, has a digital form, and those are just basically ones and zeros that form a number 0 to 255 for every single pixel. And that's what the computer works with. It doesn't actually work with colors or anything. It works with the ones and zeros at the end of the day. That's kind of like the foundation of it all. And in a colored image, it's actually a three-dimensional array. You've got blue pixel, you've got a blue layer, a green layer, and a red layer, and that stands for RGB, red, green, blue. And each one of those colors has its own intensity. So basically, a pixel has three values assigned to it. Each one of them is between 0 and 255. And therefore, you can find out what this image, what color exactly this pixel is by combining those three values. And again, computers are going to be working with that. So that's the foundation of it all. That's the red channel, the green channel, the blue channel. And finally, let's have a look at For instance, an example, a very trivial example of a smiling face in computer terms, if we just really simplify things instead of having from 0 to 255, instead of having those values, just so that we can understand things better and really grasp the concepts, we're going to say 0 is white, 1 is black, right? So we're just going to simplify things to the extreme, and you will see that that image can be represented like that. So the reason why we've brought this up is because we're going to, all of our intuition tutorials, we're going to structure on images like this, which are very simple, but at the same time, then all of those concepts can translate back to the 0 to 256 range of values, and everything applies the same way there. And the steps that we're going to be going through with these images are step number 1, convolution, step number 2, max pooling, step number 3, flattening, and step number 4, full connection. And I can imagine that probably none of these words mean much to you at the moment, but by the end of this section of the course, you will understand them in great detail and exactly what they're doing. So we'll get started in the next tutorial. For now, the additional reading that you might want to look into is Jan LeCun's original paper that gave the rise to convolutional neural networks. It's called Gradient-Based Learning Applied to Document Recognition. You may have seen this image before floating around the internet. It is from that paper. So if you want to go back to the very beginnings of how it all happened, where it all came from, this is the paper to look into. And I look forward to seeing you on the next tutorial. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. In the previous tutorial, we found out what convolutional neural networks are all about. And today we're going to dive into step 1, convolution. So this is the convolution function. I know we try to stay away from mathematics and keep things intuitive, but I couldn't help but share this formula with you because it is so simple. A convolution is basically a combined integration of two functions, and it shows you how one function modifies the other or modifies the shape of the other. And if you've done any signal processing or electrical engineering or a profession where signal processing is required, you would have inevitably come across the convolution function. It is quite popular. Now, once again, we're going to keep the mathematics light or keep them separate. And if you'd like to get into the math behind the convolutional neural networks, a great additional read is Introduction to Convolutional Neural Networks by Jianxin Wu, who is a professor at the Nanjing University in China. This paper was published literally days ago, like 5 or 6 days ago, and it is oriented specifically at people who are starting out, at beginners who are getting to know convolutional neural networks. So the mathematics there should be accessible. I actually emailed Professor Xianxin Wu, and he said his whole goal is to break the complex things down so that people who are new to this field can understand. And also he mentioned that he's got some materials available on his homepage. So if you, in the URL, if you just remove the last 2 parts and you just go to like /WJX to that part, that's his homepage, and you'll be able to find more additional tutorials and materials which haven't been published as papers, but he uses them in his tutorials. So you might find those useful. So browse around there if you'd like to get an introduction into the mathematics behind convolutional neural networks and kind of build a solid base around that area. But we're going to move on, and we're going to talk about the convolution. So what is a convolution in intuitive terms? Here on the left, we've got an input image, as we discussed. That's how we're going to look at images, just ones and zeros to simplify things. And you can see the smiley face there. Then we've got a feature detector. So a feature detector is a 3x3 matrix. Does it have to be 3x3? No, it doesn't. AlexNet, I think, uses 7x7. And then some other, one of those other famous ones uses like 5x5 feature detectors. They can be different, but usually you'll see that they are 3x3, and they are reasons to make them 3x3. So we're going to stick to the convention of having a 3x3 feature detector. Also, the feature detector is called, these are important terms because you might come across them. There are many different terms for the feature detector, but the most common ones are feature detector, or you might hear it being called kernel, or you might hear it being called filter. So in this course, we're going to be using either filter or feature detector interchangeably, but just bear in mind that it has those names. And a convolution operation is signified by an X in a circle, just as you saw in the formulas before. And here what happens is on an intuitive level, or just to think of it in terms of what is actually happening in the background rather than the mathematics, well, you take this feature detector or filter and you put it on your image like you see on the left. So you cover the, for instance, in this case, the top left corner, the 9 pixels in the top left corner, and you basically multiply each value by each value, so respective value. So the top 0 by the top left value by the top left value, then basically position number 1 1 by position number 1 1, position by number, or 0 1 by 0 1, 0 2 by 0 2, and so on. So just it's element wise multiplication of these matrices, and then you add up the results. So in this case, nothing matches up, so it's always either a 0 by 0 or 0 by 1, so the result is 0. Here you can see that one of them matched up. The one on the left matched up, and therefore we got a 1. Here nothing matched up, nothing matched up, nothing matched up. Then we move on to the next row. So and the step at which we're moving this whole filter is called the stride. So here we have a stride of 1 pixel. So here you can see again something matched up. The bottom right corner matched up. Again, stride, bottom one in the middle matched up. Here top right one matched up, then nothing matched up. The stride is 1. You can change the stride. You can make it 1, 2, you can make it 3, whatever you like. Conventionally the one that works well is usually a 2, so that's what people stick to, and we'll talk about what the stride is towards the end of this tutorial. So here we've got we're matching up, so we just keep going. Oh, here you can see we've got a 2 because 2 of them matched up, and so on and so on, so on. And there we go. There's another one that matched up. There we go. And there we're done. So what have we created, right? A couple of important things here. The image on the right is called a feature map. Also has several terms. It also can be called sometimes a convolved feature. So when you apply a convolution operator to something, it doesn't become convoluted, it becomes convolved. And yes, sometimes I think to myself in the wrong way, but it's the correct term is convolved. It's a convolved feature, or it can also be called the activation map, but we're going to be calling it a feature map in this course. So it can be called any one of those things. And what have we done here? Well, as you can see, we've reduced the size of the image. That's number one. And that's the important thing I wanted to mention about your input image and the feature detect and the stride, right? If you have a stride of 1, you can see the image reduced a bit. But if you have a stride of 2, the image is going to reduce more. So the feature map is going to be even smaller. And that's a very important function of the feature detector of this whole convolution step, is to make the image smaller because it'll be easier to process it, and it'll be just faster. It'll be just faster because imagine, like here we've got a 7 by 7 image, but imagine if you have a proper photo, right? Or you have like a 256 by 256 pixel image. It's a huge number of pixels, right? 256 squared, or like let's say you have a 300 by 300 pixels. So we don't get confused with the RGB 256. Let's just say like we have a 300 by 300 image in terms of size in pixels. Then you have 300 squared number of pixels. That's a huge number, and therefore feature detectors will reduce the size of the image, and therefore stride of 2 is actually beneficial. But then the question is, do we lose information? Are we losing information when we're applying the feature detector? Well, some information we are losing, of course, because we have less values in our resulting matrix. But at the same time, the purpose of the feature detector is to detect certain features, certain parts of the image that are integral. And so, for instance, if you think about it this way, like the feature detector has a certain pattern on it. The highest number in your feature map is when that pattern matches up. In fact, the highest number you can get is in a now simplified example, is when the feature matches exactly. And you can see with that number 4 we have in our feature map, that's exactly, so if you look over here, that's exactly where this feature detector, because there's only 4 ones in it, matched perfectly. So you can see this part over here. So the feature was detected here. And as we discussed at the very start of this section, that is, features is how we see things, is how we recognize things. We don't look at every single pixel, so to speak, in what we see on an image or in real life. We don't look at every single pixel. We look at features. We look at the nose, the hat, the feather, the eyes under, or the little black marks under the cheetah's eyes, to distinguish it between a cheetah and a leopard, or the shape of the train. We don't to distinguish it between a bullet train and a normal train, and so on. So we don't look at everything. We look at features, and that's what we're preserving, and that's what the feature map helps us preserve. Actually, that's what it allows us to bring forward and get rid of all of the unnecessary things that even as humans we don't process. There's so much information going into your eyes at any given time, like gigabytes of information. If you look at every single dot, if not terabytes of information going into your eyes per second, and still we're able to process that because we get rid of what is unnecessary. We only focus on the important features that are important to us. And that is exactly what the feature map does. So now moving on, this is our input image, and we create a feature map. So the front one, let's say the front one is the one we just created. But then how come there's many of them? But we create multiple feature maps because we use different filters, right? And that's another way that we preserve lots of the information. So we don't just have one feature map. We look for certain features, and then or basically the network decides through its training, and this is something we'll discuss towards the end of this section, through its training, it decides which features are important for certain types or certain categories, and it looks for them, and therefore it'll have different filters, and we'll talk about filters just now, but basically it'll apply these filters. So to get this feature map, it applied a filter like the one we saw, but then to get this feature map, it applied a different filter. To get this feature map, it applied a different filter, and so on. And so basically it just creates these feature maps. And actually that's why personally I think the term feature detector is better than filter. So remember over here we have this filter, which we also can call a feature detector. Well, actually the word feature detector I think is better suited. And the reason for that is that's what the purpose is, right? We don't want to just filter out our image, but even though that's the same, just a question of terminology. But basically, we want to detect features. All right, in this layer, we're going to, or in this feature map, we've detected where certain features are in the image. In this feature map, we've detected where certain other features are, where a certain specific feature is located. In this feature map, we've detected where a certain other feature is located on the image. So that's what we're doing, and let's have a look at a couple of examples. So here we're using, and this is from gimp.org, their documentation. It's a free like a kind of tool like Paint, and you can use it to adjust your images or work with your images. But basically, they have some valuable examples in their documentation, and here they have a picture of the Taj Mahal, and you can choose which filter you want to apply. So if you download this program and you upload a photo into it, and then you can actually start a convolution matrix and apply filters, and you will see that these convolution matrices are actually applied in image processing and design and so on. So let's have a look at what we get. So if we apply this filter, 5 in the middle, -1, -1, -1, -1, you can see that it sharpens the image. And yeah, so it's quite intuitive if you think of it. So 5 is the pixel, the main pixel, like in the middle of the filter or the feature detector, and then -1, -1, -1 just kind of like reduces the pixels around it in an intuitive sense. Then blur. So basically, it takes gives equal significance to all of the pixels around the one in the center, and therefore it combines them together and you get a blur. Edge enhance. So here you can see that -1 and 1, and then you get zeros, right? So you remove the pixels around the main one in the middle, and you only keep this one at a -1, and it gives you an edge. And this one's a bit harder to understand how it works, like probably harder just to think of it intuitively. Edge detect, right? So this one probably makes more sense, right? You take the middle one, you reduce the middle one, probably like the strength of the middle pixel, and then you look for the ones, you look for these ones, you increase the strength of the ones around them, so you have the ones there. Yeah, so that gives you like an edge detection, and you can see what you get there. Emboss, another one. So the key here is that it's asymmetrical, and you can see the image becomes asymmetrical as well. So you got like that kind of feeling that it's standing out towards you, and that's what you get when you have like minuses here and pluses here. Again, this is getting a bit technical now, but at least we can get some kind of intuitive understanding. Let's just go quickly through them again. So there's sharpen, there's blur, there's edge enhance, there's edge detect, there's emboss. And so as you can see, these are great examples of the same image, but we're getting feature maps. So we use different feature detectors to get different feature maps of the same image. And therefore now we have lots of this versions of this image, where in each one we've tried to detect certain things. These terms, they're not applicable to us. Except like emboss is probably not applicable to us in terms of convolutional neural networks, but edge detect, that's important. We want to detect the edges. Edge enhance, probably not. Blur, sharpen. So certain things like edge detect is probably the most important one for our type of work. And in terms of understanding, like computers, they will decide for themselves. Their neural network will decide for itself what's important, what's not, and it probably won't be even recognizable to the human eye. You won't be able to understand what those features mean, but the computer will decide. And that's the beauty that of neural networks, that they can process so many different things and understand without even having that intuition, without having that explanation why. They will understand which features are important to them, whether we have a name for them or not. That's an irrelevant question for the artificial neural network. And my favorite one, here's a image of Geoffrey Hinton, a photo of Geoffrey Hinton passed through one of these filters. All right, so that brings us to the end of today's tutorial. I hope you enjoyed learning about convolution. The key takeaway is that convolution, the primary purpose of a convolution is to find features in your image using the feature detector, put them into a feature map, and by having them in a feature map, it still preserves the spatial relationships between pixels, which is very important for us to, because if they're completely jumbled up, then we've lost the pattern. And at the same time, it is important to understand that most of the time, the features a neural network will detect and use to recognize certain images and classes will mean nothing to humans, but nevertheless, they work. And that's what convolution is, and I look forward to seeing you on the next tutorial. Until then, enjoy deep learning. Hello and welcome to the section on convolutional neural networks. Super excited that you're joining us for this section as well. And today we're going to cover off the plan of attack, how we're going to learn everything in this section. There's so much to learn. Let's see how we're going to approach this. All right, what we'll learn in this section. First of all, we'll talk about what convolutional networks actually are. Very important to understand the end goal that you're working towards before you actually start working towards it. So we'll talk about features, we'll have a look at a few little examples, we'll compare the human brain to artificial neural networks in terms of image recognition. So it'll be a fun, light tutorial to get us started for this whole section. Then we'll talk about step 1, diving straight into it, convolution operation. So this part of the course contains several steps that we need to go through in order to build a convolutional neural network, and that's how these tutorials are going to be broken up. So this one's going to be step 1, the convolution operation. We'll learn everything about feature detectors. We'll talk about which are also filters. We'll talk about feature maps and what are the different parameters there, what they mean, and we'll have a look at some visual examples as well. Then we'll talk about step 1, part B, the ReLU layer, which is the rectified linear unit. And we'll talk about why linearity is not good and how we want more non-linearity in our network for image recognition. Then we'll talk about step 2, pooling, and we'll understand how pooling works. We'll talk specifically about max pooling, and we'll also mention a couple of things about mean pooling or sum pooling and other approaches that you can take to the process of pooling. Also in this lecture, we'll have a really cool example. So there'll be a very visual interactive tool that we're going to look at. So make sure to stick around to the end of that lecture, because that's going to add a lot of value to your learning process, what we're going to discuss at the end there. Step 3, flattening. So here it's going to be a quick tutorial on how to proceed from your pooled layers to your flattened layer. And then we're going to talk about full connection. So this is the very meaty tutorial that puts everything together and puts everything into perspective and actually shows you how everything works at the end of the day and how those final neurons understand how to classify your image. Very, very important tutorial. And hopefully that will summarize or kind of put everything together for you. And finally, we'll have a summary which will summarize everything we've talked about. And as an extra little feature, I've included a tutorial on softmax and cross entropy. So you don't have to take this tutorial, but I thought it would be a great addition of knowledge, because these are terms that you will come across when dealing with convolutional neural networks. So maybe take it right away. Maybe when you come across these terms, you will always know you can come back to this course and take this tutorial to understand better what softmax and cross entropy are. And also, as always, throughout these tutorials, there will be lots of recommended reading for you to further upskill and get more knowledge. And on that note, I can't wait to see you on the first tutorial. This is going to be a very fun and exciting section. And until next time, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about ReLU, which is the rectified linear units. And this is an additional step on top of our convolution step. So it's not a separate big step, it's a small step. It's step 1b basically. And what is going on here? Well, we have our input image, we have our convolution layer, which we've discussed. And then on top of that, we're going to apply, wait for it, our favorite rectifier function. And you're already familiar with the rectifier function from the previous section on artificial neural networks. And so sometimes authors or instructors separate the convolution and the rectifier as two separate steps. In our examples, we're just going to consider them just one big step. First the convolution, then the rectifier. And the reason why we're applying the rectifier is because we want to increase non-linearity in our image, or in our network, in our convolutional neural network. And rectifier acts as that filter, or acts as that function which breaks up linearity. And the reason why we want to increase non-linearity in our network is because images themselves are highly nonlinear, especially if you're recognizing different objects next to each other, or just on backgrounds and stuff like that. Like, the image is going to have lots of nonlinear elements, and the transition between pixels, adjacent pixels, is often going to be nonlinear. That's because there's borders, there's different colors, there's different elements in your images. But at the same time, when we're applying a mathematical operation such as convolution running this feature detection to create our feature maps, we risk that we might create something linear, and therefore we need to break up the linearity. So let's have a look at an example. Here is an original image. Now, when we apply a feature detector to this image, we get something like this. So you can see here that black is negative, white is positive values. Well, when you apply a feature detector to a proper image, which has not just zeros and ones, but has lots of different values, and you apply, as we saw previously, feature detectors can have negative values in themselves. Sometimes you'll get negative values. And here, their black ones are negative, white ones are positive. And what a rectified linear unit function does is it removes all the black, right? Anything below 0 it turns into 0. And so from this, it turns into this, right? And so it's pretty hard to see what exactly is the benefit in terms of breaking up linearity. I'll try to explain. I'll try to like show an example on this image, but at the end of the day, this is a very mathematical concept, and we would have to go into a lot of math to really explain what is going on. But let's try. Let's have a look. So, for instance, let's look at this building here, right? So this is a building on its own. Then you can see this shadow, this black part, this shadow over here. Well, you can see that it's white, the reflection of the light, and then it's a gray, and then it gets darker, and then it gets darker again, right? So, and when we take it out, we take out that black part. So think of it in terms of linearity, right? So it looks like when you go from white to gray, the next step would be black, right? The next step would be black. It's a linear progression from bright to dark, and therefore this is kind of like a linear situation. When you take out the black, you break up the linearity. Let's try another one. Let's have a look here. And at the same time, it's still that same building, right? It's not like you're it's not like you're blending two buildings into each other. But that is secondary. The main point is breaking up the linearity. So let's have a look here. Same thing. So you see white, gray, black, gray, white. And when you break it up, you don't have that anymore, right? You don't have that progression, the gradual progression, that you just have like an abrupt change, and that helps introduce non-linearity into your image. It's a very rough explanation, very kind of like on the fingers explanation, rather than technical, but hopefully it kind of helps you understand a bit better what we're talking about here. So here again, you can see white, gray. This is a better example even. You see bright, darker, 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 darker. So this part looks like it's linear, then you break it up like that. Again, so this is a very rough explanation. It's not absolutely perfect, but at least it gives you some idea of what's going on. But if you'd like to learn more, there's a good paper. As always, there's always a paper. This one is by C.C.J. Kuo from the University of California, and it's called Understanding Convolutional Neural Networks with a Mathematical Model. And basically there he answers two questions, and you need to just look at the first one, and the question is why a nonlinear activation function is essential at the filter output of all intermediate layers. So that kind of explains it in a bit more detail, both in terms of intuition and mostly in terms of mathematics. So that's an interesting paper where you can get some more additional information on this topic. And if you really want to dig in and explore some cool stuff here, then there's another paper that you might be interested in. It's called Delving Deep into Rectifiers Surpassing Human Level Performance on Image and Net Classification. And here the authors, Kai-Ming He and others from Microsoft Research, they propose a different type of rectified linear unit function. They propose the parametric rectified linear unit function, which you see here on the right, and they argue that it delivers better results without sacrificing performance. So interesting read if you'd like to get a bit more into this topic. And that's all for today. The ReLU layer is pretty simple, pretty straightforward, just applying the rectifier function. And I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about max pooling, and we've got some very exciting slides coming up ahead and even a special surprise at the very end of the tutorial. So let's get started. The first question is, what is pooling and why do we need it? Well, to answer that question, let's have a look at these images. On these three images, we've got a cheetah. In fact, it is the same exact cheetah. On the first image, the image is positioned properly, and the cheetah is looking straight at you. On the second image, it's a bit rotated, and the third image is a bit squashed. And the thing here is that we want the neural network to be able to recognize the cheetah in every single one of these images. In fact, this is just one cheetah. What if we have lots of different cheetahs? Here's a cheetah, here's a cheetah, here's another cheetah, here's a cheetah, here's a cheetah, and here's a cheetah. And we want the neural network to recognize all of these cheetahs as cheetahs. And how can it do that if they're all looking in different directions, they're all in different parts of the image, they're like their faces are positioned in different parts of the image. Somebody's on the right hand side, somebody's in the left corner, somebody's in the middle. They're all a bit different. The texture is a little bit different. The lighting is a bit different. There's lots of little differences. And so if the neural network looks for exactly a certain feature, for instance, a distinctive feature of the cheetah is the tears that are on its face going from the eyes, or the shadows that look like tears, the texture, the pattern that is going from its eyes down its on the sides of its nose that looks like tears, that's a distinctive feature of the cheetah. But if it's looking for that feature which it learned from certain cheetahs in an exact location or an exact shape or form or texture, it will never find these other cheetahs. So we have to make sure that our neural network has a property called spatial invariance, meaning that it doesn't care where the features are located. Not so much as in which part of the image, because we've kind of taken that into consideration with our map, with our convolution layer, but it doesn't have to care if the features are a bit tilted, if the features are a bit different in texture, if the features are a bit closer or if features are a bit further apart relative to each other. So if the feature itself is a bit distorted, our neural network has to have some level of flexibility to be able to still find that feature. And that is what pooling is all about. So let's have a look at how pooling works. Here's our feature map. So we've already done our convolution, and we've completed that part, and now we're working with the convolution layer. Now we're going to apply pooling. So how does it work? We're going to be applying max pooling. There's several different types of pooling you can apply. There's mean pooling, max pooling, sum pooling, and we'll comment on those towards the end of this tutorial. But for now, we're just applying max pooling. So we take a box of 2 by 2 pixels like that. And again, it doesn't have to be 2 by 2. You can choose any size of box. And again, we'll comment on that towards the end of the tutorial. And you place it in the top left-hand corner. And you find the maximum value in that box. And then you record only that value. And you disregard the other 3. So in your box, you have 4 values. You just disregard 3. You only keep 1, the maximum, which is 1 in this case. Then you move your box to the right by a stride. You select the stride once again. So here, we've selected a stride of 2. And that's what you normally select. You can select a stride of 1, you can select, so there are overlapping boxes, you can select any kind of stride that you like, even 3 if you want, but we're selecting a stride of 2 here, and that's what is commonly used. And then you repeat the process, you record the maximum. Here, if you cross over, it doesn't matter, you just continue doing what you're doing, so you still record the maximum here, 0. Here the maximum is 4, here the maximum is 2, here the maximum is 1, 0, 1, 0, 2, and then 1. So as you can see, a few things happened. First of all, we still were able to preserve the features, right? The maximum numbers, they represent, because we know how the convolution layer works, we know that the maximum or the large numbers in your feature map, they represent where you actually found the closest similarity to a feature. But by then pooling these features, we are, first of all, getting rid of 75% of the information that is not the feature, which is not the important things that we're looking out for. Because we're disregarding 3 pixels out of 4. So we're only keeping 25%. And then also, because we are taking the maximum of the pixels that or the values that we have, we are therefore accounting for any distortion. So for instance, 2 images in which, for the example, the cheetah's tears on the eyes are, in one image they're a bit to the left or a bit rotated to the left, and in the other one they're a bit, and they're how they're supposed to be, or how we like if we take one as the basis and in the other one they're a bit rotated to the left, the pooled feature will be exactly the same. So you can see here, if we are talking about the cheetah's tears, then let's say this is the 4 and this is where it was here, then if it was a bit rotated, so for instance the 4 ended up over here, then when we're doing the pooling, we're still going to get the same pooled feature map. And that's kind of the principle behind it. It's a very rough explanation, again, intuitive explanation, but that's the point of pooling, that we're still being able to preserve the features and moreover account for their possible spatial or textural or other kind of distortions. And in addition to all of that, we're reducing the size. So there's another benefit. So we're preserving the features, we're introducing spatial invariance, we're reducing the size by 75%, which is huge, which is really going to help us in terms of processing. And moreover, another benefit of pooling is we're reducing the number of parameters. So we're reducing, again, by 75%, we're reducing the number of parameters that are going to go into our final layers of the neural network. And therefore, we're preventing overfitting. It is a very important benefit of pooling that we're removing information, and that is a good thing. That is a good thing because that way, our model won't be able to overfit onto that information, especially because that information is not relevant. Remember, like at the very start, we were talking about even for us as humans, it's important to see exactly the features rather than all this other noise that is coming into our eyes. Well, same thing for neural networks. By disregarding the unnecessary, non-important information, we're helping with preventing of overfitting. So there we go. That is what pooling is about. And the question here is, of course, why max pooling, right? There's lots of different types of pooling, and why a stride of 2, why a size of 2 by 2 pixels, lots of all these things. And on that note, I'd like to introduce you to this lovely research paper called Evaluation of Pooling Operations in Convolutional Architectures for Object Recognition by Dominik Scherer from University of Bonn. There's the link. And the beauty about this paper is that it's very, very simple, very straightforward. So if you've never read a research paper before, but you'd like to give it a go, this is a great place to start. It's very short, only 10 pages, very easy to read. And plus, the extra benefit is that now that we've discussed convolution and pooling, you will be totally comfortable with everything that they're talking about in this paper. And this is a great way to actually reinforce your knowledge. So I highly recommend checking this paper out. It'll take 20 minutes to read it. And you can even skip part 2, which is called related work. If it feels a bit far-fetched or alienating, just don't read that part. Just go straight from part 1 to part 3. And one thing that you do need to know about this paper, they talk about a concept called subsampling. Well, subsampling is basically average pooling. So remember how here we were taking the maximum. So in our square, we were taking the maximum value. There's a concept called mean pooling or sum pooling. Sum pooling is you just sum these values up. Average pooling or mean pooling, you take the average value out of all of these. And subsampling is kind of like a generalization of mean pooling. It's a more kind of generalized approach to taking the average of these values. And you can read a bit more about it in the paper, but otherwise just think of it as average pooling when you're reading that paper. And so that's where you can get some additional information on this topic. And now kind of let's recap. Where have we gotten to? So there's our input image. Then we applied the convolution operation and we got the convolution layer. And now to each of those feature maps that we get, we've applied the pooling layer. So we've done these 2 steps, convolution and pooling. And now we're going to do something very fun, something exciting. We're going to experiment with this. So this is a screenshot I took from a tool created by Adam Harley from back when he was at Ryerson University of Computer Science, and now he's at Carnegie Mellon, I think, doing his PhD. And a great tool. So let's open up. Let's have a look. So you can find it. You can't actually find it through Google. You have to know the URL. It's just hard to find it through Google because there's no text here. Just this URL, scs.ryerson.ca, and then this stuff on the end. And basically, this is exactly what we're doing, but visualized. So here, you need to draw a number. So let's say I draw a number 4. And this tool will put the number 4 here. That's your image in our first step. Then this is the convolution step, right? And this is the pooling step. And also pooling, by the way, is also called downsampling. So pooling and downsampling are the same things. So you can see it's applied convolution, then it's applied pooling, and you can see how it exactly works. So you can see what kind of convolutions it has applied, or what kind of filters it applied, what they look like. You can see what features it's looking out for. And then it's applying pooling, so it's reducing the size. And you can see here that this is important, right? So you can see that this is the convolved image, and this is the pooled image, and you can still see the same features. It's just less information, but same features, right? The features are preserved. That's the important part. And moreover, if our 4 was a bit to the kind of like rotated a bit to the side, it would still be able to pick up very similar pooled layers. And then after that, it's got more layers. We haven't talked about that yet. So then it's got another convolution layer here, which we actually won't have. And then it has another pooled layer, but it's basically just repeating that same process. And then after that, this is what we're going to be talking further down in the course. It's got the fully connected layers and so on. But you can definitely play around with that. So if I delete that, if I draw a 7, you'll see that it actually tells you the guesses. It guesses that this is a 7, and the second likelihood is a 3. So you can draw it some challenging things and see if it can pick them up. So let's say if I draw something that looks like a 0, but it's not a finished 0, will it pick it up? No, this time didn't pick it up. It looks like a 9 to the image. What if I kind of like finish it like that? See, now it thinks it's a 0 or a 9. And you can see over there what's lighting up, the 0 or the 9. But we'll talk about that part further down. Let's do one more. Let's say like 8. I think 8s are pretty hard for this. No, picked up an 8. So you can see that goes into an 8. And then like after that, it stops being recognizable. It stops making sense to us humans, right? These features that it's working with. But at the same time, it is correctly recognizing that it's an 8. Yeah, so definitely play around with that. You can draw a smiley face, see what happens then. Looks like a 3 to this tool, because the tool is obviously trained up only on digits from 0 to 9. So it has to recognize something there out of those, and it recognizes a 3. It's like in life when you see something like a type of fruit that you've never seen before, like a custard apple or something, and you think that it's a pear, because you've never actually seen one before. You don't know what to classify it as. Same thing here. So it hasn't actually trained on smiley faces, and that's why it thinks it's a tree. It's a 3. So there you go. It's a very powerful tool. It'll be helpful for you to play around with it. Actually, when you put your mouse over a pixel, it shows you where the feature detector was to pick up that pixel. So you can see where this pixel is coming from, and also, so you can see how the filter was kind of like going through the image, exactly how we talked about in the course. And here you can see the pooling. You can see that the pooling is done with a little square size of 2 by 2, and you can see that it's a stride of 2 as well, just as we discussed in today's tutorial. So there you go. Have a play around with that, and I hope you enjoyed today's session. I look forward to seeing you next time, and until then, enjoy deep learning. Hello and welcome back to the course on deep learning. I hope you're tracking along with these intuition tutorials just fine, and that you had a chance to play around with everything we've learned so far. And today we're talking about flattening, and the good news is that this is a very simple step, and this tutorial is going to be very quick, and then we'll be able to move on to the next interesting things. All right, so far we've got the pooled layer, pooled feature map, and that is after we apply the convolution operation to our image, and then we apply pooling to the result of the convolution, or to the convolved image. And so what are we going to do with this pooled feature map? Well, we're going to take it and we're going to flatten it into a column. So basically just take the numbers row by row and put them into this one long column. And the reason for that is because we want to later input this into an artificial neural network for further processing. So this is what it looks like when you have many pooling layers, or you have the pooling layers with many pooled feature maps, and then you flatten them, so you put them into this one long column sequentially, one after the other, and you get one huge vector of inputs for an artificial neural network. And so to sum all of this up, we've got an input image, we apply a convolution layer, and let's not forget the ReLU, or rectified linear units function, that we apply after the convolution layer as well. And then we apply pooling, and then we flatten everything into a long vector, which will be our input layer for an artificial neural network. And exactly how that works, we'll find out in the next tutorial. Hope you enjoyed today's session, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're finally at step number 4, full connection. So what is this step all about? Well, in this step, we're adding a whole artificial neural network to our convolutional neural network. So to all of the things that we've done so far, which are convolution, pooling, and flattening, now we're adding a whole new ANN on the back of that. How intense is that? That is something. That is definitely something. And so here we've got the input layer, we've got a fully connected layer and output layer. And by the way, the fully connected layer, in the artificial neural networks, we used to call them hidden layers. And here we're calling them fully connected layers because they are hidden layers, but at the same time, they're a more specific type of hidden layers. They're a fully connected layer. In artificial neural networks, hidden layers don't have to be fully connected, whereas in convolutional neural networks, we're going to be using fully connected layers, and that's why they're generally called fully connected layers. And so basically that whole column or vector of outputs that we have after the flattening, we're passing it into the input layer. And here we've got a very simplified example just for illustration purposes. And what the main purpose of the artificial neural network is to combine our features into more attributes that predict the classes even better. So we already, in our vector of outputs in the flattened result from what we've already done, we have some features encoded in the numbers in that vector. And they can already do probably a pretty good job at predicting what class we're looking at, whether it's a dog or a cat, or whether it's a tumor or not a tumor, and so on. But at the same time, we know that we have this structure called the artificial neural network, which is designed, which has a purpose of dealing with attributes and coming up, or dealing with features and coming up with new attributes and combining attributes together to even better predict things that we're trying to predict. And we know that from the previous part, so why not leverage that? And that's exactly what the plan here is. So how about we pass on those values into an artificial neural network and let it even further optimize everything that we're doing. And so that's what we're going to be doing, but let's look at a more realistic example because this one is a bit too simple. So here we've got a better looking artificial neural network where we have 5 attributes on the input. Then we have, in the first hidden layer, we have 6 neurons. In the second, fully connected layer, we have 8 neurons, and then we have 2 outputs, one for dog and one for cat. And so an important thing to for us to talk about here is that why do we have 2 outputs? We are kind of used to having only one output in our artificial neural networks. Well, one output is for kind of when you're predicting a numerical value, when you're running a regression type of problem. But when you're doing classification, you need an output per class, except for the exception is when you have just 2 classes. Like we have 2 classes here, dog and cat, and we could have just done one output and made it a binary output and said 1 is a dog and 0 is a cat. And that would have worked totally fine. And actually, in fact, you'll see Hadlan do that in the practical tutorials, and that's how they'll be structured. But at the same time, if you have more than 2 categories, for instance, dogs, cats, and birds, then you have to have a neuron per every category. And that's why we're going to practice with 2 categories in this example so that we know what to expect if we ever have more than 2 categories. And so what's going to be happening here? So we've already done all the groundwork. We've done the convolution, we've done the pooling and the flattening, and now the information is going to go through the artificial neural network. So let's have a look at how all that all happens. There's the information going through from the very start, from the moment when the image is processed, then convolved, then pooled, flattened, and then through the artificial neural network, all 4 steps. And then a prediction is made. And we'll see how this happens in a moment. It'll be very, very interesting. But for now, let's just say a prediction is made, and for instance, 80% that it's a dog. But it turns out to be a cat. And then an error is calculated, what we used to call a cost function in a artificial neural network and we use the mean squared error there, or in convolutional neural networks, it's called a loss function, and we use a cross entropy function for that. And we'll talk about cross entropy and mean squared errors in a separate tutorial and how all that happens. But for now, let's just say we have a loss type of function which tells us how well our network is performing, and we're trying to optimize it or minimize that function to optimize our network. So the error is calculated, and then it's back propagated through the network, just like we had in the artificial neural networks. It's back propagated, and some things are adjusted in the network to help optimize the performance. And the things that are adjusted are, as usual, the weights in the artificial neural network part, so the blue lines that you see here, the synapses. Then also another thing that is adjusted is the feature detectors. So we know that we're looking for features, but what if we're looking for the wrong features? What if this didn't work out because the features are incorrect? And so the feature detectors, remember those little matrices that we had, the 3x3 matrices, they are adjusted so that maybe next time it'll be better, and let's see what happens, type of thing. But of course, it's all done with a lot of science in the background, with a lot of math, and it's all done through a gradient descent with backpropagation. So it's all not just random perturbations. It's actually very thought through how it's done. But nevertheless, the feature detectors are adjusted, the weights are adjusted, and this whole process happens again. And then again, the error is backpropagated. And this keeps going on and on and on. And that's how our network is optimized. That's how our network trains on the data. So the important thing here is that the data goes through the whole network from the very start to the very end. Then the error is compared. So the error is calculated and then is backpropagated. So same story as with artificial neural networks, just a bit longer because of that for the first three steps that we already had. And now let's have a look at the interesting part, the really interesting part. How do these two classes work? Or how do these two output neurons work? Because before we've always kind of had one output neuron. What happens when we have two? How does this situation of classification of images play out? Well, let's start with the top neuron first. We're going to start with the dog. The main purpose, what we need to do first is we need to understand what weights to assign to all of these synapses that connect to the dog, so that we know which of the previous neurons are actually important for the dog. And let's see how that is done. So let's say, hypothetically, we've got these numbers in our previous layer, previous fully connected, or in the final fully connected layer. And again, these numbers can be absolutely anything. They don't have to be that. They can be any numbers. But just for argument's sake, we're going to agree that we are looking specifically at numbers between 0 and 1. So it's easier for us to argue these things and understand. And 1 means that neuron was very confident that it found a certain feature. And 0 is going to mean that that neuron didn't find a feature it's looking for. So because at the end of the day, these neurons, like anything else on this left side, is just looking at features at an image. This is already very, very processed, but still, it's detecting a certain feature or combination of features on the image, right? Before in the convolve step, we had kind of recognizable features. In the pool step, they're less recognizable. Then they become even less recognizable in the flattened image, and then they get combined and so on. But nevertheless, we're talking about here certain features that are present in the image or their combination. So a 1, which is being passed, and this is important, is being passed to both the dog and the cat at the same time, to both the output neurons. So a 1 means that for our argument, it means that this neuron is firing up. It's really rapidly detecting that feature that might be an eyebrow. It might be detecting this eyebrow for simplicity's sake, is detecting this eyebrow, and it's communicating that to the dog neuron, to the cat neuron, saying, I can see my eyebrow, I can see my eyebrow. And then it's up to the dog and the cat neuron to understand what that means for them, right? And so in this case, which neurons are firing up? These 3 neurons are firing up. The eyebrow, and let's say the nose, is saying, I can see a big nose, and I can see floppy ears. So it's saying that to the dog and to the cat. And then what happens is we know that this is a dog. So the dog neuron knows that the answer is it is actually a dog. Because at the end we're comparing to the picture or to the label on the picture, and it knows a dog. So basically the dog neuron is going to say, aha, so I should be triggered in this case. So these are my neurons. They're telling this signal that they're sending to me, to the dog, and to the cat is actually a indication for me that it is a dog. And throughout these lots and lots and lots of iterations, if this happens many times, the dog will learn that these neurons do indeed fire up when the feature belongs to a dog. On the other hand, the cat neuron will know that it's not a cat, and it will know that this feature is firing up, and this neuron is telling me it can see floppy ears, floppy ears, floppy ears, but at the same time, it's not a cat. So basically, to me, that's a signal that I should ignore this neuron. And the more that happens, the more the cat neuron is going to ignore this neuron about the floppy ears. And so basically, that's how, through lots and lots of iterations, if this happens often, so this is just one example, but if this happens often, maybe a 1, maybe a 0.8, 0.9, maybe sometimes it won't fire, but overall, on average, this neuron is lighting up very often. When it is indeed a dog, the dog neuron will start attributing higher importance to this neuron. And so there we go. That's how we're going to signify it. We're going to say that these 3 neurons, through this iterative process with many samples and many epochs. Remember, so a sample is a row in your data set, and epoch is when you go through your whole data set again and again and again. Through lots and lots of iterations, this dog neuron learned that this eyebrow neuron and this big nose neuron and this floppy ear neuron, they all seem to really contribute very well to the classification of what it's looking for, and which is a dog. So that's how it works. And again, these ears and nose and eyebrows, those are very, very approximate or like very far-fetched examples, because by this stage in this whole convolutional neural network, it is completely unrecognizable what they're looking for. But at the same time, it is something in the features of dogs or cats or whatever you're classifying. And then, so let's move on to the next one. Now we're going to look at the cat neuron. But these, we're going to remember that these weights are, we've sorted out the dog. So the dog is kind of like pretty much ignoring all these other neurons, 1, 2, 3, 4, 5, but it's really paying attention to what these 3 neurons are saying. Now, what is the cat listening to? Well, whenever it is actually a cat, right? This is an example of a situation when it's actually a cat. So you'll see that these 3 neurons, 0.9, 0.9, and 1, they're saying something. They're saying something to both the dog and the cat, and this is again important to remember. So this output signal goes both ways. It's the same, right? It's saying 1 to the dog, it's saying 1 to the cat. But then it's up to the dog and to the cat to decide whether to take into account that signal and learn from it or not. And both the dog and the cat can see that this is a photo. I should have put a photo of a cat here, but basically imagine a photo of a cat. Both the dog and the cat can see that this is actually a cat. So basically the dog is like, oh, okay, so these whiskers and these pointy triangle ears and this small size, I guess, or I don't know, oh, maybe this type, you know how cats have these things in their eyes? Their eyes are like little, they're not circles, they're lines or something like that, like cat eyes. Basically, these cat eyes, they're definitely not working for me. They're not helping me out predict, because every time these neurons light up, the prediction is not what I'm looking for. On the other hand, the cat is like, that's interesting. Every time this one lights up, or most of the time it lights up, it matches my expectation. It matches what I'm looking for. Okay, I'm going to listen to this guy more. Then this one, same thing. Every time it lights up, or most of the times it lights up, I happen to be rewarded for my prediction because I get it right. It's a cat. Okay, so I'm going to listen to him more. This one, useless to me because he's not actually, he's not even lighting up. It's a cat, but he's not lighting up. So the opposite is happening. And this one as well, it's a cat, but he's not lighting up. So I'm not going to listen to him. But this one, what was this? The cat eyes light up. I can see that it's a cat. It matches most of the time, so I'm going to learn from that, and I'm going to listen to these 3 guys more often than not. And so basically the cat is listening to these three and it's ignoring the other five. And that is how these final neurons learn which neurons in the final fully connected layer to listen to. So the output neurons learn which of the final fully connected layer neurons to listen to. And that's how they understand. Basically, that's how the features are propagated through the network and conveyed to the output. And so even though these features, of course, don't have that much meaning to them, like floppy ears or whiskers, at the same time, they do have some distinctive, they are a distinctive feature of that specific class. And that's how the network is trained, because we also, during the backpropagation process, we also adjust the feature detectors. So if a feature is useless to the output, it's going to probably be disregarded, because this doesn't happen over one or two iterations. This happens through thousands and thousands of iterations. So with time, a feature that is useless to the network is going to be disregarded and replaced with a feature that is useful. And so at the end of the day, in this final layer of neurons, you are likely to have lots of features or combinations of features from the image that are indeed representative or descriptive of dogs and cats. And so then once your network is trained up, this is how it's applied. So this is the next step. Like, we've already trained up our network. Well, let's see what happens when this network is applied. So let's say we pass on an image of a dog. The values are propagated through a network. We get certain values. And so this time, the dog and the cat neurons don't know. They don't have the image of the dog here. They don't know that it's a dog or a cat. They have no idea what it is. But they have learned to listen to what is being shown here, right? They have learned to listen to, the dog neuron listens to these three neurons, the cat neuron listens to these three. And so the dog neuron looks at 1, 2, 3 and says, aha, these are pretty high, so my probability is going to be high that it's a dog. The cat neuron looks at these three and says, okay, this one is pretty high, but these are pretty low. Interesting, so my probability is going to be 0.05. And that's where you get your prediction. So then your first choice for this neural network is dog, second choice is cat, and that's pretty much it. So the answer is dog. And same thing happens when you pass an image of a cat. You get new values, and you can see that even though this one's high, these ones are low, and for the cat, this one's high, and this one's a bit low. So the probability here might not be as great as previously, but still you can see that it's a cat with 79%, and so therefore the neural network is going to vote that it's a cat. And so basically, the neural network is going to conclude that it's a cat. Voting is a term that is used for these guys. So these neurons in the final fully connected layer, they get to vote, and these are their votes. And again, we are just, for argument's sake, putting values between 0 and 1 here. These could be any values, but they get to vote, and then these weights are the importance of their vote. So this is these purple weights are how the dog neuron views their votes, how much importance it assigns to these neurons and to those votes, and this is how much importance the cat neuron assigns to these to the votes of these neurons. And so these neurons vote. The dog and the cat, based on their learned weights, they decide who to listen to, and then they make their predictions, and the whole neural network concludes that this is, in this case, a cat. And then that's your conclusion. And that's how you get images like this, where you have a cheetah, and then you have a cheetah class with like a high probability. So this is the probability that the network has predicted, and these are lows. But these still exist because there's still kind of like a small chance the other neurons are also listening to their voters, and they're saying, oh, maybe it's actually a leopard. And a bullet train, very, very probable. Here, scissors, this one won, but hand glass was very close, second, and then frying pan stethoscope, because you could see like these guys, this neuron, the scissors neuron, the output scissors neuron, listened to its voters, and it had the predominant vote overall, but then the hand glass had a good outcome as well. So there we go. That's how the full connection works and how this all plays out together. I hope you enjoyed today's tutorial. We're going to summarize all of this in the summary as well, and I'll see you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. So we've learned quite a lot in this section of the course. Let's summarize what we've talked about. All right, so here we go. We started with an input image. to which we applied multiple different feature detectors, or also called filters, to create these feature maps. And this comprises our convolutional layer. Then on top of that convolutional layer, we applied the ReLU, or rectified linear unit, to remove any linearity or increase nonlinearity in our images. Then we applied a pooling layer to our convolutional layer. So from every single feature map, we created a pooled feature map. And basically, the pooling layer has lots of advantages. The main purpose of the pooling layer is to make sure that we have spatial invariance in our images. So basically, if something tilts or twists or is a bit different to the ideal scenario, then we can still pick up that feature. Plus, pooling significantly reduces the size of our images. And also, pooling helps with avoiding any kind of overfitting of our data or of our model to the data, because it just simply gets rid of a lot of that data. But at the same time, pooling preserves the main features that we're after, just because the way it's structured, and the pooling we used was max pooling. Then we flattened all of the pooled images into one long vector or column of all of these values, and we input that into an artificial neural network, and that was step 3, flattening. And step 4 is the fully connected artificial neural network, where all of these features are processed through the network, and then we have this final layer, final fully connected layer, which performs the voting towards the classes that we're after. And then all of this is trained through a forward propagation and back propagation process, and lots of iterations and epochs. And in the end, we have a very well defined neural network. And another important thing is not only the weights are trained in the artificial neural network part, but also the feature detectors are trained and adjusted in that same gradient descent process. And that allows us to come up with the best feature maps. And in the end, we get a fully trained convolutional neural network, which can recognize images and classify them. So there we go. That's how convolutional neural networks work. And now you should be totally comfortable with this concept and ready to proceed to the practical applications. If you'd like to do some additional reading, then there's a great blog by Edith Deshpande from 2016. You can see the link over there at the bottom. So the blog is called The 9 Deep Learning Papers You Need to Know About Understanding CNNs Part 3. And this blog actually gives you a short overview of 9 different CNNs that have been created by people like Jan LeCun and others, which you can then go ahead and study further. So there will be a lot of new things that will be totally new to you and that you will have to get your head around. But just keep this blog in mind, or these 9 papers in mind. And even if you're not ready to go through them right now, maybe after the practical tutorials, maybe after you do some additional training in the space of deep learning, slowly you can then reference these works. And ideally, I think you will get a lot of value through looking through other people's neural networks and how they structured their convolutional nets. And that will help you understand what are the best practices and why people did certain things in a certain way. And that will help you with your architecture of neural networks, because neural networks and convolutional neural networks are not an exception. They are like an architecture challenge. You have to come up with a idea and then structure it and then adjust it and tweak it to get the best possible design and the best possible and optimal performance. So there we go. That's us for today. I hope you enjoyed today's tutorial and this whole section, and I look forward to seeing you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. This is an additional tutorial to talk about the softmax and cross entropy functions. It is not 100% necessary in order for you to go through all of the parts that we've been through in the main part of this section, where we're talking about the convolutional neural networks. But at the same time, I thought it would be a good addition to your bag of knowledge and skill set. So let's go ahead and dig into these functions. So to start off with, what we have here is the convolutional neural network that we built in the main part of the section. And then at the end, it pops out some probabilities for 0.95 for a dog and 0.05 or 5% for a cat, given that photo in the left as an input. This is after the training has been conducted. This is actually, it's running, and it's classifying a certain image. And so the question here is, how come these two values add up to 1? Because as far as we know from everything that we've learned about artificial neural networks, there is nothing to say that these two final neurons are connected between each other. So how would they know what the value of how would each one of them know what the value of the other one is, and how would they know to add their values up to 1? Well, the answer is they wouldn't in the classic version of an artificial neural network. And the only way that they do is because we introduce a special function called the softmax function in order to help us out of the situation. So normally what would happen is the dog and the cat neurons would have any kind of real values. They don't have to they don't have to add up to 1. But then we would apply the softmax function, which is written up over there at the top, and that would bring these values to be between 0 and 1, and it would make them add up to 1. And to quote Wikipedia, the softmax function, or the normalized exponential function, is a generalization of the logistic function that, quote unquote, squashes a k-dimensional vector of arbitrary real values to a k-dimensional vector of real values in the range of 0 to 1 that add up to 1. So basically, it does exactly what we want. It brings these values to be between 0 and 1 and makes sure that they add up to 1. And the way it works is that the way that this is possible is that because at the bottom over here you can see that there's a summation. So it takes the exponent and puts it in the power of z and adds it up. So z1, z2 across all of your classes, all of these values. And so that's your normalization happening right there. So that's how the softmax function works, and it makes sense to introduce a softmax function into convolutional neural networks, because how strange would it be if you had a possible classes of a dog and a cat, and for the dog class you had probability of 80%, and for the cat class you had a probability of 45%, right? It just doesn't make sense like that, and therefore it's much better when you introduce a softmax function, and that's what you will find happening most of the time in convolutional neural networks. Now, the other thing is that the softmax function comes hand in hand with something called the cross-entropy function, and it's a very handy thing for us. So let's first look at the formula. This is what the cross-entropy function looks like. We're actually going to be using a different calculation. We're going to be using this representation of the cross-entropy, but the result's basically the same. This is just easier to calculate. And what I know this might sound very unrelated to anything right now, just formulas on your screen, but there will be some additional recommended reading at the end of this section. So don't worry if you're not picking up on the math, like if we haven't explained the math right now. But the point here is that what is the cross-entropy? Well, a cross-entropy function, remember how we previously in artificial neural networks, we had a function called the mean squared error function, which we used as the cost function for assessing our network performance. And our goal was to minimize the MSE in order to optimize our network performance. Well, that was our cost function then, and in convolutional neural networks, we can still use MSE, but a better option in convolutional neural networks, after you apply the softmax function, turns out to be the cross-entropy function. And in convolutional neural networks, when you apply the cross-entropy function, it's not called the cost function anymore, it's called the loss function. And they're very similar, they're just little terminological differences and a bit different in what they mean. But for our purposes, it's pretty much the same thing. And what happens is the loss function is, again, something that we want to minimize in order to maximize the performance of our network. So let's have a look at a quick example on how this function can be applied. So let's say we've put an image of a dog into our network. The predicted value for dog is 0.9, and this is during the training. So we know the label that it is a dog. So the predicted value is 0.9. The predicted value for cat is 0.1. Then here we have the label, so we know it's a dog because this is training, and 1 for dog, 0 for cat. And so in this case, you need to plug these numbers into your formula for the cross entropy. So how you would do it is the values on the left go into the variable q, the one that is under the logarithm on the right side, and the values from the right would go into p. And so it's important to remember which one goes there where, because if you get them wrong, you don't want to be taking a logarithm from a 0 value or a logarithm from a 1. So you just want to plug them in, make sure you plug them into the correct places, and then you basically add that up. So that's how the cross entropy works. And we'll look at actually right now we're just going to look at a specific step-by-step example of applying this function in real life, and it'll kind of make more sense what cross entropy is, and it'll be less like my goal in this tutorial is to make you more comfortable with cross entropy, because it can sound very convoluted and no pun intended. It can, like convolutional neural networks, it can sound very complex, right? Scary, but it's not. That's the point. So let's go ahead and apply it just so we know that it's not scary. So here's neural net, and also this will explain why we're doing this, why we're looking at different cost functions. So neural network 1, neural network 2. Let's say we have 2 neural networks, and then we pass an image of a dog. And we know that this is a dog and not a cat. And then we have another image of a cat, this time an animal, and it's a cat, not a dog. And here we have a weird looking animal, which is in fact a dog, not a cat, if you look very closely. So we want to see what our neural networks will predict. In the first case, neural network 1, 90% dog, 10% cat, correct. Neural network number 2, 60% dog, 40% cat, still correct. Worse, but correct. Second option, first neural network, 10% cat, dog, 90% cat, correct. Neural network number 2, 30% dog, 70% cat, worse, but still correct. And then finally, neural network 1 in image 3, neural network 1, 40% dog, 60% cat, incorrect. Neural network number 2, 10% dog, 90% cat, incorrect, and worse. So the key here is that even though both networks got it wrong in the last one, throughout all 3 images, neural network 1 was outperforming neural network 2. So even in the last case, it was very it gave dog like a 40% chance, as opposed to neural network 2 only gave dog a 10% chance. So neural network 1 is outperforming across the board when compared to neural network 2. And so now we're going to look at the functions that they can measure performance that we've kind of talked about already. So let's put these into a table. So there's neural network 1. You have the row number, so that's the image number. And then for image 1, you have what it predicted, 90% dog, 10% cat. So those are the hat variables. And then you have the actual values. So dog correct, cat incorrect. Same thing for image number 2, and same thing for image number 3. And same for neural network number 2. So dog 60%, cat 40% in the first image. That's what it predicted. The correct answer was dog, not a cat, and so on. And so now let's see what errors we can actually get. So what errors we can calculate to estimate the performance and monitor the performance of our networks. So one type of error is called the classification error. And that is basically just asking, did you get it right or not? Regardless of the probabilities, it's just, did you get it right or did you not get it right? So in both cases, for both neural networks, each of them, they got 1, or so this is how many they got wrong. So they got 1 out of 3 wrong. So 33% error rate for neural network 1 and 33% error rate for neural network 2. And so basically from this standpoint, both neural networks perform at the same level. But we know that's not true. We know that neural network 1 is outperforming neural network 2. That's why classification error is not a good measure, especially for the purposes of backpropagation. Mean squared error, different. And by the way, I did these calculations in Excel. I just didn't want to bore you with them, but you can totally just sit down and do them on a paper or in Excel. These are very straightforward calculations. Just basically take the sum of squared errors and then just take the average across your observations, and that's pretty much it. So for neural network 1, you get 25%. For neural network 2, you get 71% error rate. So as you can see, this one is more accurate. It's telling us that neural network 1 has a much lower error rate than neural network 2. And then cross entropy, again, we've seen the formula. You can also calculate this. This is actually even easier to calculate than the mean squared error. Cross entropy gives you 38% for neural network 1 and 1.06 for neural network 2. So you can see the results are a bit different when you look at them like that, when you look at the mean squared error and cross entropy. The question of why would you use cross entropy over mean squared error isn't just about the kind of like the numbers that they spit out. These calculations were just to show you that this is all, it's all doable. You can just do it on a paper. It's not, these are not very intense mathematics. These are pretty simple, straightforward things. But the question of why would you use cross entropy over mean squared error, it's a very, very good question to ask. I'm glad you asked it. The answer to that is, like, there's several advantages of cross entropy over mean squared error, which are not obvious. And so I'll mention a couple, but then I'll let you know where you can find out more. So one of them is that if for instance, you're at the very start of your backpropagation, your output value is very, 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 very tiny, very tiny. So it's much smaller than the actual value that you want. Then at the very start, the gradient in your gradient descent will be very, very low, and it won't be enough. It'll be very hard for the neural network to actually start doing something and start moving around and start adjusting those weights and start actually moving in the right direction. Whereas when you use something like the cross entropy, because it's got that logarithm in it, it actually helps the network assess even a small error like that and just do something about it. Here's how to think about it. So let's say, again, this is very intuitive approach. There's going to be a link to the mathematics, and you can derive these things through the mathematics in more detail, but a very intuitive approach. Let's say your outcome that you want is 1, and right now you are at 1 millionth of 1, right? 0.000001, and then you improve next time. You improve your outcome from 1 millionth to 1,000th, and in terms of if you calculate the squared error, you're just subtracting one from the other, or basically in each case you're calculating the square error, and you'll see that the squared errors, when you compare one case versus the other, it didn't change that much. You didn't improve your network that much when you're looking at the mean squared error. But if you're looking at the cross entropy, because you're taking a logarithm and then you're comparing the two, dividing one by the other, you will see that you have actually improved your network significantly. So that jump from 1 millionth to 1,000th in mean squared error terms will be very low. It will be insignificant, and it won't guide your gradient boosting process or your backpropagation in the right direction. It will guide it in the right direction, but it'll be like a very slow guidance. It won't have enough power. Whereas if you do it through cross entropy will understand that, oh, even though these are very small adjustments that are just making a tiny change in absolute terms, in relative terms it's a huge improvement, and we are definitely going in the right direction. Let's keep going that way. So cross entropy will help your neural network get to the optimal state. It's a better way for the neural network to get to an optimal state. But bear in mind that this only works when the cross entropy is only the preferred method only for classification. So if you're talking about things like regression, like which we had in artificial neural networks, then you would rather go with mean squared error, whereas cross entropy is better for classification. And again, it has to do with the fact that we're using softmax functions. So that's a kind of intuitive explanation of that. A good place to learn a bit more about that, if you're really interested in, why are we using cross entropy versus mean squared error, Google a video by Jeffrey Hinton called the softmax output function. And he explains it very well. And, being the godfather of deep learning, who can explain it better anyway? And by the way, any video by Jeffrey Hinton is golden. He's just got a huge talent for explaining things. Anyway, so that's softmax versus cross entropy. I hope that gives you kind of like an intuitive understanding of what's going on here, but more importantly, that you're not put off by the term cross entropy, because Hadelin will mention it in the practical tutorials, and I wanted to make sure that you're prepared for that. And it's just another way of calculating your loss function and another way of optimizing your network, which is specifically tailored to classification problems and therefore convolutional neural networks, and comes in hand in hand with the softmax function. So, additional reading. If you'd like a light introduction into cross entropy, if you're interested in cross entropy a bit more, of course, a good article to check out is called A Friendly Introduction to Cross Entropy Loss by Rob DiPietro, 2016. Here's the link below. Very, very nice, very soft, no super complex math. Good analogies, good examples. He uses analogies of cars, and you look at cars and talks about information and bits and restrictions, and how would you encode this, how would you encode that. It's a good article to have a look at, and will give you a good overview of cross entropy, like from an introductory standpoint. If you want to dig into the heavy math, like what you see here, then check out an article or a blog by How to Implement a Neural Network Intermezzo 2. So intermezzo is like an intermediary thing, like a intermittence in, like when you go to a theater and you have like a break between the first part and the second part. So that, because he's like going through all these steps, and then he says, oh, I got to explain this first. And yeah, so that's why it's called intermezzo. No other reason, as far as I understand. The article is by Peter Rowlands, 2016 as well. So both are quite recent. And yeah, check out this if you would like to dig into the mathematics behind cross entropy, behind softmax and cross entropy in this article, actually. So there we go. That's all there is to these two. Hopefully I was able to add some additional clarity, and good luck with that. It's going to be fun, and enjoy the practical tutorials. I'll see you next time. Until then, enjoy deep learning.